All program officers, stand by, IT ready. Pak Agus, please play the video.
Indonesia is a beautiful archipelago country with a tropical climate and an enormous natural resource. Forests and their biodiversity are the most valuable natural resources and the natural capital of Indonesia. The forest area in Indonesia continues to shrink. The accelerated population growth has caused forest exploitation in fulfilling the demand for wood raw materials, both legally and illegally. While this demand keeps increasing, the wood supply continues to decline. Wood is a raw material that is greatly useful and valuable for humanity. It is used for construction materials, furniture, handicrafts, firewood, and a variety of household uses. Founded in 2002, the Research Center for Biomaterials, Indonesian Institute of Sciences, has been conducting research in natural materials, such as wood and natural fibers. The center also focuses on developing processes, technology, and design to produce value-added products. The Modification and Engineering of Biomaterials Research Group focuses on characterizing and modifying lesser-value wood materials into more valuable products. This research group works closely with another research group called Biocomposites Engineering and EcoStructure. They've been working on engineering wood-based materials and natural fibers, such as bamboo, into functional composite materials. This research group also works on building material design and providing a technology package of an eco-friendly home, known as EcoHouse. All parts of the EcoHouse use eco-friendly composite materials. It also utilizes an architectural concept that conserves electrical energy. One of the research interests of the Biomass Process Technology and Bioremediation Research Group involves the utilization of lignocellulosic materials, such as non-wood natural fiber, and incorporating their conversion process to create bioenergy or bioethanol. Lignocellulosic materials can also be used as a medium for making enzymes that are used in bioremediation processes. These waste-degrading enzymes can be used to remove color and toxic materials present in textile waste. This research group is also developing derivative products such as wood adhesives made from natural latex. These adhesives do not produce emissions of harmful substances. They are friendly to human health and the environment. The Urban Agricultural Pest Management Research Group has focused their research on maintaining the quality of the wood commodity and protecting cellulose-based products from the attack of pests such as insects and fungi. By utilizing natural materials such as plant extracts and microorganisms, this research group has been developing eco-friendly urban and agricultural bioinsecticides and studying their biocontrol approaches through laboratory bioassays as well as behavioral and ecological studies. research outcome is part of this group's efforts to tackle the process of biodeterioration that is caused either by wood-attacking insects or wood rot fungi. Through a series of chemical, biological, mechanical, and physical processes, natural materials can be transformed into biopolymers, bioactive compounds, conventional composite materials, advanced and ingenious materials, as well as other products that are eco-friendly. In addition to providing high economic value products, natural-based materials can also be converted into renewable fuels as substitutes for fossil fuels. Appointed as the Center of Excellence for Lignocellulose, the Research Center for Biomaterial also has an ISO IEC 9001-2008 certification for quality management systems. It also serves as an appointed urban agricultural pest testing laboratory authorized by the Pesticide Commission of the Indonesia Ministry of Agriculture. Since 1996, the Research Center for Biomaterials has been a satellite office for foreign cooperation between LIPI with Kyoto University, Japan. The center is also active in research programs in Asia, such as JSPS and SATREPS. In addition, the Research Center for Biomaterials has been cooperating with various research institutions, universities, and industry from home and abroad. The Research Center for Biomaterials continues to develop advanced materials and bioproducts through a series of processes in order to support a clean and healthy environment. The Research Center for Biomaterials, Indonesian Institute of Sciences, appointed as a center of excellence, continuously advances innovation in addressing global challenges.
Okay, so ladies and gentlemen, good morning, local time in Indonesia, and welcome to everyone. For those of you who are already joined with us in the Zoom meeting, I can see now we have around 131 participants. So I would like to just announce that we are about to begin our event today. And we will start at 10 a.m. local time in Indonesia. So in the meantime, we will wait for everyone to join with us, both in the Zoom meeting or through the live streaming in the LIPI YouTube channel. So maybe one reminder is that you can also rename your Zoom meetings name with for the presenters and participants, and you can see the guidance in the chat room right now. So we will wait for everyone to join with us. So you still have some time to prepare yourself, and thank you very much for your attention.
Indonesia is a beautiful archipelago country with a tropical climate and an enormous natural resource. Forests and their biodiversity are the most valuable natural resources and the natural capital of Indonesia. The forest area in Indonesia continues to shrink. The accelerated population growth has caused forest exploitation in fulfilling the demand for wood raw materials, both legally and illegally. While this demand keeps increasing, the wood supply continues to decline. Wood is a raw material that is greatly useful and valuable for humanity. It is used for construction materials, furniture, handicrafts, firewood, and a variety of household uses. Founded in 2002, the Research Center for Biomaterials, Indonesian Institute of Sciences, has been conducting research in natural materials, such as wood and natural fibers. The center also focuses on developing processes, technology, and design to produce value-added products. The Modification and Engineering of Biomaterials Research Group focuses on characterizing and modifying lesser-value wood materials into more valuable products. This research group works closely with another research group called Biocomposites Engineering and EcoStructure. They've been working on engineering wood-based materials and natural fibers, such as bamboo, into functional composite materials. This research group also works on building material design and providing a technology package of an eco-friendly home, known as EcoHouse. All parts of the EcoHouse use eco-friendly composite materials. It also utilizes an architectural concept that conserves electrical energy. One of the research interests of the Biomass Process Technology and Bioremediation Research Group involves the utilization of lignocellulosic materials, such as non-wood natural fiber, and incorporating their conversion process to create bioenergy or bioethanol. Lignocellulosic materials can also be used as a medium for making enzymes that are used in bioremediation processes. These waste-degrading enzymes can be used to remove color and toxic materials present in textile waste. This research group is also developing derivative products such as wood adhesives made from natural latex. These adhesives do not produce emissions of harmful substances. They are friendly to human health and the environment. The Urban Agricultural Pest Management Research Group has focused their research on maintaining the quality of the wood commodity and protecting cellulose-based products from the attack of pests such as insects and fungi. By utilizing natural materials such as plant extracts and microorganisms, this research group has been developing eco-friendly urban and agricultural bioinsecticides and studying their biocontrol approaches through laboratory bioassays as well as behavioral and ecological studies. The research outcome is part of this group's efforts to tackle the process of biodeterioration that is caused either by wood-attacking insects or wood rot fungi. Through a series of chemical, biological, mechanical, and physical processes, natural materials can be transformed into biopolymers, bioactive compounds, conventional composite materials, advanced and ingenious materials, as well as other products that are eco-friendly. In addition to providing high economic value products, natural-based materials can also be converted into renewable fuels as substitutes for fossil fuels. Appointed as the Center of Excellence for Lignocellulose, the Research Center for Biomaterial also has an ISO IEC 9001-2008 certification for quality management systems. It also serves as an appointed urban agricultural pest testing laboratory authorized by the Pesticide Commission of the Indonesia Ministry of Agriculture. Since 1996, the Research Center for Biomaterials has been a satellite office for foreign cooperation between LIPI with Kyoto University, Japan. The center is also active in research programs in Asia, such as JSPS and SATREPS. In addition, the Research Center for Biomaterials has been cooperating with various research institutions, universities, and industry from home and abroad. The Research Center for Biomaterials continues to develop advanced materials and bioproducts through a series of processes in order to support a clean and healthy environment. A Research Center for Biomaterials, Indonesian Institute of Sciences, appointed as a Center of Excellence, continuously advances innovation in addressing global challenges.
Okay, thank you for waiting. We also just watched the precious message from us, the committee, for everyone, for our honorable keynote speakers, invited speakers, all the presenters, participants who give us your big support for us and show the excitement to join this event. Right now it is still raining in Bogor City, so it is a very touching moment for all of us this morning. But anyway, we are very excited to continue today's event, and we hope that all of you are truly enjoy our event today. So, Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, good morning local time in Indonesia, and welcome to the first international conference of Lignocellulose in conjunction with the 10th International Symposium for Sustainable Humanosphere 2021. I'm Fanny Clara Ardiati, and it is a pleasure to be your host today. So today is the second and also the last day of our event of conference and symposium, which is organized by JSPS Alumni Association of Indonesia in collaboration with Research Center for Biomaterials, National Research and Innovation Agency, BRIN, Republic of Indonesia. We would like to address our big appreciation for all the stakeholders who give their big supports to this event from JSPS Bangkok Office, Thailand, LAPAN, BRIN Indonesia, RISH-Kyoto University, Japan. We would like to also thank our valuable partners for their supports from many national universities in Indonesia, from IPB University, Padjajaran University, Islamic University of Indonesia, and Trisakti University. We also would like to thank our valuable partners from even far away in Sumatera and Kalimantan, from Jambi University, Lambung, Mangkurat University, Mulamarwan University, and University of Sumatera Utara. But before we begin, I would like to invite and appreciate everyone if you can turn on your camera so that we can see all of us here today, maybe to see your colleagues and everyone here. So, but please kindly remain turned off your audio during this morning session. Thank you. First of all, let me give a very warm welcome to our honorable guests who are already joined with us and will join with us today. To Professor Yoshio Otani as the Director of JSPS Bangkok Office. To Professor Masato Shiotani from RISH-Kyoto University, Japan. Also to Professor Kenji Umemura from RISH-Kyoto University, Japan. Also to Professor Dr. Ernasri Adiningsih as Acting Director of National Institute of Aeronautics and Space, National Research and Innovation Agency, BRIN. To Dr. Iman Hidayat as Acting Director of National Institute of Life Sciences, BRIN. To Dr. Akbar Hanif Dawam as the Head of Research Center for Biomaterials, BRIN. And to Dr. Didi Tarmadi as the Chairman of Icon-Lig and ISSH 2021. And not forget to also mention for our 13 honorable invited speakers who give us their supports by sharing their knowledge and giving us their lectures in this today's event. I would like to send my greetings for those our honorable invited speakers who are already joined with us today, to Dr. Wendy Harjupa from Center for Atmospheric Science and Technology, National Institute of Aeronautics and Space, BRIN. Also to Dr. Muhammad Haswan Husip from University Science Malaysia, and to Professor Dr. Wahyu Duyanto and Dr. Hoirul Himi from Research Center for Biomaterials BRIN, who already joined with us today in this morning. And also welcome to all distinguished guests and participants. Thank you for joining us today. So in the annual event of ISSH, together with our first international conference of lignocellulose, now we bring up the topic of frontier innovation of lignocellulose and humanosphere sciences towards sustainable development goals and climate change mitigations. So for today's agenda, we will start by two presentations from our keynote speakers. And after that, we will proceed to the parallel sessions with all the invited speakers and presenters. To begin today's event, let me invite our first keynote speakers. So for Professor Masato Shiotani from Research Institute for Sustainable Humanosphere, Kyoto University, Japan, who will deliver the first presentation. So to Professor Masato Shiotani, please, time is yours.
Thank you very much. Just a moment, I should bring my presentation material. Can you see and hear my presentation?
Yes, Prof, it's very well.
Okay, so my name is Masato Shiotani, the director of the Research Institute for Sustainable Humanosphere, Kyoto University. Today, I'd like to talk a general story about the humanosphere sciences. And in the first part, I'd like to show some general idea and which we are now aiming at as a research institute. And in the latter part, I'd like to show one good example of the humanosphere sciences, I believe, which is kind of characterized as a diagnosis and remediation of the Earth. So what is the humanosphere sciences? So as I said, that it is characterized as the diagnosis and remediation of the Earth. So we define the humanosphere as the sphere that supports human activities, including human living environment and forest sphere, the atmosphere, and the space environment. So here, just a moment. This is a cover page of a brochure of our research institute, and it's said the RISH and the space environment and atmosphere and forest sphere and the living environment. This is also described in the left panel. So we are trying to investigate to present the future programs of the humanosphere and explore innovative technology that will contribute to establishing a sustainable society in harmony with the natural environment. Actually, our English name of our institute is Research Institute for Sustainable Humanosphere. So I think the sustainability is one very important keyword here in the RISH. So why do we need such a sciences, kind of interdisciplinary sciences? So we are now facing the several hazardous events threatening the existence of humankind. So now we're facing the global warming, and it is becoming tangible, and consequently, with the disasters are intensified. And also, long distance communication is providing us kind of infectious diseases in the world that's becoming highly prevalent. So these problems are, just a moment. Okay. So this picture in the right down should be movie, but it's not moving. I'm sorry about that. So these problems are very complex in nature, and therefore only deepening academic knowledge in a scientific area cannot answer these complicated problems. So we need to investigate our expert knowledge in various areas with an interdisciplinary view. Okay, here. So this is one example of the last very heavy rainfall in the southern island of Japan, Kyushu Island. And so we had very serious problems after this, during this event. So humanosphere science is a kind of a subset or related, very closely related to the sustainability science. And the Sustainability Development Goals, SDGs, a collection of 17 interrelated goals designed to be a blueprint to achieve a better and more sustainable future for us. And the SDGs was set to, just a moment, sorry about this one. So SDGs was set in 2015 by the United Nations General Assembly and intended to be achieved by the year 2030. They are included in the United Nations resolution called the 2030 Agenda for what is colloquially known as Agenda 2030. And so our research institute, RISH, can not all, but the wide range of this, the SDG goals. And so we should keep our mind to the output toward the public and also the political area as a scientific achievement. So in our institute, we set 5 missions. By integrating the research result, we pursue solutions to present the future progress concerning the humanosphere. So mission 1 is environment diagnosis and regulation of circulatory function, and mission 2, advanced development of science and technology toward a solar energy society. Mission 3, sustainable space environment for humankind, and mission 4, development and utilization of based sustainable materials in harmony with the human living environment. And mission 5 is closely related to the quality of the future humanosphere. So I'm not going in detail about these mission items, but we set those missions to achieve our goal. Our research institute, RISH, is also characterized as the Joint Usage Research Center. So we need to tackle these interdisciplinary problems in a new academic area. We have to have a good research materials or research instrument. So here we have several very unique instrument or facilities to investigate the humanosphere sciences. And also we have a database that is for open use for the public. And also we are doing a project type collaborative research for promotion of collaborative projects. And as a part of our RISH activities, in 2016, we initiated a new program named Humanosphere Azure Research Node, ARN, so which is trying to strengthen the hub function of international collaboration, collaborative research, and fostering innovation in humanosphere science with the ultimate goal of delivering solution on a global scale. So this is focused in the Southeast Asian countries, and also people living in South Asian countries, scientists in South Asian countries, and also we have an equatorial atmosphere later in the Indonesia. So we are utilizing the facilities and the human relation for the further humanosphere sciences. We have a promotion video, or we made a promotion video last year, but I don't have enough time to show during my presentation. So if you are interested in our activities in RISH, please visit here. This is our website, and you can easily find this video, and you can see or enjoy our promotion video. So in the following, I would like to show one historical example related to the humanosphere sciences, I believe. So this is an event, or this is a case about the ozone depletion. Ozone is mostly located in the upper atmosphere, and that is that produced the Antarctic ozone hole. So atmospheric ozone had been exceptionally depleted in the stratosphere over the Antarctic during spring of Southern Hemisphere. This was first documented in 1985, almost 35 years ago. And scientists performed extensive measurement from ground-based sensors and satellite and aircraft, so very complementary and complicated way. So they're trying to describe this event very minutely, or in that sense, that globally. So based on these observations, the theoreticians proposed mechanisms for the depletion. And they finally concluded it is due to the release of the man-made chlorofluorocarbons and other halocarbons. And so the scientists resolved the kind of this very important question. And most importantly,
Kapan ya? Besok? Direbus dulu nggak sih biasanya, Pak? Kalau MFTIR gitu?
And most importantly, this result is contributing to establish international kind of the structure, Montreal Protocol, that is an international treaty designed to protect the ozone layer by phasing out the production of ozone depleting substances. And the final line that the import that is taken from the recent scientific ozone assessment report, ozone depletion scientific ozone assessment report. And in the first important sentence, they said that the actions taken under the Montreal Protocol have led to decreases in the atmospheric abundance of controlled ozone depleting substances, and the start of the recovery of ozone, stratospheric ozone. So this is a very important message. And you may not know detail about the ozone hole, and you are now living very healthy, not problem world. But this is kind of realized under this Montreal Protocol, I can say. So I will just introduce some history of the ozone hole discovery and some investigation, and also some achievement of such an investigation. So this is an observation that Harebe is located in the Antarctic, supported by British Antarctic Survey. And this is the time total ozone section. So this shows the total ozone time series during the October from the end of 1950s and the middle of 1980s. And up to middle of 1970s, the ozone amount is rather flat, not so changing. But after that, the ozone is quickly decreasing in the Antarctic area. And here, the author Farman showed the fluorocarbon amount. So the axis is shown that the increasing in the down bay, and so the fluorocarbon is increasing, and at the same time the ozone decreasing. So they pointed out the relation between the decrease of ozone and the fluorocarbon. And this is also confirmed in the satellite observations. So this is the monthly mean total ozone in October observed by total ozone mapping spectrometers. And they use the South Polar projections with the pole indicated by a cross and the 30 degrees south latitude by dashed circles. And so we see some ozone small area here over the South Pole or the Antarctic area. And here the number is 270 and 240, 210. And finally, in 1985, 180. So the ozone is rapidly decreasing during this season. So this is also confirmed with the kind of in situ observations using the ozone sonde. So the sun ozone instrument is here, and this is launched with use of this big balloon. And by the way, this is an observation at the South Pole, supported by the United States of America. And usually we see the ozone amount is like this, so we can see some ozone layer here. But in 1992, October 11th, or in 1993, October 12th, we see almost nothing of ozone here in the height range of 15 to 20 kilometers. So this is the actually affected by the total ozone. I didn't say about the unit of total ozone, but the total ozone is a kind of accumulation or integrated amount of ozone. So the ozone is highly depleted in the ozone layer here, in this case in around 50 to 20 kilometers. So such a decreasing trend is continuing in the 1990s. And so such an ozone hole is deepening and deepening. And here there are actually 4 South Antarctic stations, South Pole, Harebe, and the Japanese station Showa. And so it's very critical and hazardous to human. And the mechanism of the ozone hole is very closely related to the polar stratospheric clouds. So I'm not going in detail about the mechanism, but on the polar stratospheric clouds, there happened the heterogeneous reaction in the surface of cloud droplet, and it is very important to release the chlorine compound originally from the chlorofluorocarbons. So here is a schematic diagram of the mechanism of ozone hole. And I'm not going in detail about this mechanism, but here you can see the chlorine compound. There are many chlorine-related compound, and this chlorine is originally from the chlorofluorocarbons. So chlorofluorocarbon itself is very stable atmospheric constituent, but if so, the sheer chlorofluorocarbons going up to the very high altitude, it is photochemically dissociated, and so they release the chlorine, and such a chlorine is affected on the ozone depletion in the springtime of the Antarctic regions. So after the discovery of the ozone hole, several supporting the observations have been done. So this is one example done by the airplane, and this is very simple for the latitude and ozone, and also the CLO. CLO is a product that indicating the ozone. So the probably flight going from low latitude to the high latitude. So we see the clear ozone depletion around 64 or 5 degrees south. And at the same time, CLO is increasing. That indicate the chlorine is a very critical destroyer of the ozone here in the Antarctic stratosphere. So this is also the result from the satellite, and we are focusing on the first, the upper right picture. This is an ozone observation done by the satellite. So instrument name is MLS, and we see, so actually this is the almost South Pole. The black area is not the data. This indicates the no data area, so this is not clear data presented here. And we see the rather small ozone here, and at the same time we see the enhancement of CLO here, and we can say that the chlorine that is originally from the chlorofluorocarbon is destroying the ozone over the Antarctic in the lower stratosphere. So in such a critical condition, the international community established the Montreal Protocol, which is an international treaty designed to protect the ozone layer. So this is a diagram showing the time and equivalent stratospheric chlorine. So how much the chlorine is released in relation to the chlorofluorocarbons. And if we if we don't have such a protocol, the chlorofluorocarbon amount is released. So the release amount is very rapidly. And so as suggested in Montreal Protocol, this is slightly decreased. So this is a kind of, so we should do this, but it's not so strong. So after that, there are several corrections of this future projection, and now we are in the sense of the zero emission in 2011 about the fluorocarbons. And actually the fluorocarbons, there are many variants. So, and we see that the most fluorocarbons, most of those species kind of peak and also shows some decrease here. And this is a picture taken from the recent scientific ozone assessment of ozone depletion. The first figure of the general summary. And here, this diagram shows the chlorofluorocarbon release, how the release of the chlorofluorocarbon is going in the time series. And after the Montreal Protocol, the such a release is rapidly decreasing here like this. So it's a good indicator at the first look. But as I said, that the chlorofluorocarbon is a long-lived species in the atmosphere. It's not so easily destroyed. But as I said, that in the stratosphere, it is slowly destroying. So the equivalent effective chlorine in the stratosphere is not so sharply decreasing, slowly decreasing. It takes about 100 years and so on. And corresponding to this, the decrease of the effective chlorine, the ozone is now slowly recovering. And this is a message, as I said, that here. So now we can see the start of the recovery of the stratospheric ozone. So now I'd like to show some of the computer simulations with Montreal Protocol and without Montreal Protocol. This means that if we take this route, so in that case, the scientist couldn't find answer about the atmospheric phenomenon. So scientists cannot understand why this ozone depletion is happening. So this is a no protocol case, and now we're taking this route, zero emission case. And so again, we cannot see the movie here. I'm sorry, this is a movie, but cannot show you that you can see this web page, the original version of the movie. And in the next figure, this is a summary of the time series of total ozone with and without Montreal Protocol. So with Montreal Protocol, so this is a world we are now living. So owing to the Montreal Protocol, we are now living in the very healthy Earth. And ozone amount, this is an ozone amount in early 2000 and up to 2070. So the ozone is slowly recovering, but not drastically decreasing. So the Montreal Protocol works very well. But without Montreal Protocol, so in that case, as I said, the scientists didn't understand, cannot understand the mechanism of the ozone depletion. After around here, 2020, the situation is not so big compared with Montreal Protocol. But after that, the ozone layer is catalytically destroyed. And around 2030 and also 2040, there is no ozone layer in the atmosphere. So we are very happy. So now we are living in this with Montreal Protocol, but not without Montreal Protocol. So here is a summary of my talk. So the role of the Humanosphere scientist is to aim to investigate the present and future problems in the Humanosphere. So this is a kind of data diagnosis and theoretically explore treatment of these problems. This is a kind of remediation that will contribute to establishing a sustainable humanosphere. So very healthy and good condition of the Earth now. So more importantly, such results should be delivered to people in public and political sectors and implemented in proper way, like a Montreal Protocol. An example about the ozone depletion is one of the most successful demonstrations in human history. And so in collaboration with scientists and the politics and the public people, and it should make the best use of the current problems we are facing, like global warming and due to the greenhouse gases increasing. So that's all my talk. Thank you very much.
Thank you very much for Professor Masato Shiotani for the interesting topic related to our theme and the perspective of the RISH-Kyoto University, Japan. Thank you very much. Next, we will hear the second presentation from our second keynote speaker, from Professor Dr. Ernest Riyadiningsih as the Acting Director of National Institute of Aeronautics and Space, National Research and Innovation Agency, BRIN. So I would like to invite Professor Erna to deliver her presentations. So Professor Erna, please, time is yours.
Yes, thank you, MC. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. I hope you all keep healthy. Thank you so much. And first of all, I would like to thank that the organizer of this important symposiums invite me to speak on behalf of LAPAN. I would share my presentation material from my screen. Sorry. Could you see it?
Yeah, yes,
okay.
It's very
okay,
clear.
Thank you. So I would like to raise on important topics, although LAPAN as the Aeronautics and Space organizations not really dealing directly with the what you call it most of the participants here is doing in their research. I would like to raise about the importance of space-based science and technology, and to support, particularly to support sustainable development goals and climate mitigations. I would like to introduce, my name is Ernest Riyadiningsih, and at the moment I'm appointed as the acting head of a new name of LAPAN. Still we have the name of LAPAN, but the acronym is quite a bit different. You know, not a National Aeronautics and Space Institute, but we are now become Aeronautics and Space Research Organizations, and we still have the LAPAN as the name of a space agency in Indonesia, and we are now under the National Research and Innovation Agency, or BRIN. In this particular symposium, I would like to share some of the important issues on how not only our organization structure already transformed into a new form of organizations, and but facilities on the scope of our activities. And the second important is that I would like to share about the satellite, importance of satellite Earth observation, particularly to address the issue of sustainable development goals. And I would end my speech with some concluding remarks. First, I would like to to share with you about what are the core activities of the, I would not say that this is the organization, but the program, our national program in Indonesia. This is not only belong to LAPAN, but also belong to BRIN and also belong to Indonesian as the whole. The core activities of Aeronautics and Space Program in Indonesia, as mandated by Space Act number 21, 2013. This is the legal basis of the activities. And so I would like to more focus on some of these four core activities. The first core activities is related to space and atmospheric sciences, and I think most of the participants some of the participants here also dealing with the space and atmospheric sciences. And the second is in aeronautics and space technology, including rocket, satellite, and aeronautics. And the third is in remote sensing, is more for the application of the space-based technology. And we have a national remote sensing data bank and national Earth observation system. And last but not least is in the space policy studies. And from the perspective of organization that LAPAN has mandate from the Space Act from the 2013 to 2021 or this year. But since the 1st of September this year, LAPAN has been integrated, including with LIPI and other research organizations, become a bigger organization as the part of the BRIN, National Research and Innovation Agency from September this year, and so forth. And this is the facilities in conducting aeronautic and space activities in Indonesia. So this is kind of what we are going to leverage the application of the space-based science and technology, including to address SDGs and climate change mitigation as well. And with regard to satellite Earth observations, of particularly to address the sustainable development goals, first, of course, we understand, we know that there are 17 goals under the sustainable development goals. And here, some of the goals are contributed significantly by the satellite Earth observation, including the clean water and sanitation, sustainable cities and communities, climate actions, life below water, life on land. And of course, there are also some limited contribution of the satellite Earth observation to support the SDGs, such as zero hunger, good health and well-being, affordable and clean energy, in industry, innovations and infrastructures, as well as responsible consumptions and productions. I would like to share you about how the digital services of remote sensing data and information produced by LAPAN in both in a web-based platform as well as a mobile-based platform. This is including not only the data itself, but also information derived from remote sensing satellite data, as well as from other observation platform. I mean a terrestrial platform, which is also become our research activities, which is dealing with the sustainable development goals and climate change. First, I would like to share the activities that can support the SDGs number 6, which is clean water and sanitation. And we have activities in the last 2 years, this is our activities to monitor the Citarum watershed. This is located in West Java. And the goal of these activities is to internalize integrated watershed management plans that have been compiled into spatial planning. So this from this figure, we can see that the watershed area is have a very significant changes from year to year, and this is in the bottom part of these figures. We can see that in the central of the watershed now is covered with this settlement area. This is also our research activities that has been delivered to the Ministry of Environment, Forestry and Environment, or KLHK, because it's a joint activities, a national joint activities, and I think also this project also supported by the local government of West Java. Next is still under the SDGs number 6, the clean water and sanitation. We have the activity in land forest rehabilitation monitoring, still around the Citarum watershed in Java. But the goal is not only to monitor, but also to establish the action of replantations of critical land area of the Citarum. Of course, the replantation is not conducted by LAPAN. This is the project under the Ministry of Environment and Forestry from 2013 until 2017. And based on the use of remote sensing satellite data, we can monitor the progress of the replantation to rehabilitate the condition or the water quality of Citarum watershed itself. And next is some activities to support the SDGs number 11, which is sustainable cities and communities. Some of the important activities is we have done monitoring in a particular area of a big city. Some example is in the Surabaya city, East Java. And we monitor the green open space and residential area or the settlement area, and we have an analysis to correlate with the disaster risk potential, and the ultimate goal is how can we decrease the disaster risk index. Of course, this project is in collaboration with the local government, as well as the related ministries and universities in East Java. So based on the data processing, we can just separate the area of a settlement to monitor the development, the increase and decrease and so forth. And we come up with the conclusion that there is a green open space decreasing significantly over this area. And next is activities to support the SDGs number 13. This is the climate actions. There are two major activities that we have conducted so far. First is related by using the remote sensing data. We monitor the agricultural drought potential over Indonesia. So the coverage is Indonesian area as the whole, and in this activities we have a good collaboration with the Ministry of Agriculture and as well as with the other local government in particular areas of Indonesia. And the goal is how to decrease the national disaster risk index. So this is the part of how the disaster risk index could be decreased to have a potential action plan to to improve the impact on agricultural sectors in particular. And this is we combine the use of low resolution data with medium resolution data so that we come up with the information on a monthly basis. Next is still related to the activities to support SDGs number 13. But in this particular activities, we focus on the atmosphere. This is the greenhouse gases monitoring of Indonesia, in particularly carbon dioxide and methane. And the goal is we can provide the greenhouse gases emissions inventory at the national level, as well as to support the MRV, measurement, reporting, and verification. So we can see from this figure the use of NOAA data. This is the low spatial resolution, but with a very good resolution for the atmospheric parameters. And next, still related to the SDGs number 13, the climate actions, but this is the kind of combination between the space-based technology application and terrestrial-based observation. We have the LAPAN, particularly the Center for Atmospheric Science, have conducted several studies on the impacts of climate change on the coastal areas, for example, in West Java, and also the impacts on the water resources, particularly in tidal areas, and food security as well. And also it is related to vector-borne disease, and the group of the research is focused on Central Java. And the other research is on urban heat island changes and projections in Indonesia. And LAPAN, through the Center for Atmospheric Science and Technology, also has developed Indonesia Climate Change Information System. And the system, we call it Sri Rama. And the result can be used for the authority of national disaster mitigation management, as well as the authority in climatology and meteorology agencies. And this is so the output of this system is both in spatial information as well as numerical informations. Not only a current situation of the climate change and impact, but also this is another area. So this system is designed basically to conduct climate simulations and scenarios by using climate models that is called a cubic conformal atmospheric model. We can have a projection until 100 years, and the application is quite very broad, not only for the climate change study itself, but also for example, development planning, spatial planning, climate change mitigation and adaptation actions, and many sectors as shown in this figure. So this is a kind of system combining the observation system with the prediction system, as well as from the satellite-based data. And next is the activities to support the SDGs number 14. This is life and below water. And one of the activity is on a coastal aquaculture site selection monitoring in the Central Java and North Sumatra. And this research is to provide the result of this research is how we can provide the marine resources management and fisheries in the management area. One of the example is we have produced the mangrove distribution area, including its changes time to time. For example, this is the area in Segara Anakan and also in Nias Island, North Sumatra. And this is another activities dealing with the SDGs number 14, life below water. We are using the daily resolution satellite data, but with a lower spatial resolution, but we can provide the information based on the parameter of the sea surface temperature, as well as the chlorophyll content, to provide the potential fishing ground area in Indonesia. And this is quite well developed, and the users also can use this information in a mobile platform, so that the fishermen can easily utilize the information in their daily activities in fisheries or in a fishing to find a fishing ground of any particular area in Indonesia. Next is the activities related to SDGs number 15. This is life on land, and the most significant activities that already adopted by the authority in the Ministry of Forestry and Environment is the forest degradation and deforestation monitoring, by using the data to provide information on the degradation of any forest area. And this is an example in the Sumatra and Riau area. We can see the forest cover in particular area from 2016 to 2017. And what is the goal of these activities is we can achieve to extend the degraded conservation, and also we can monitor the restoration action plan conducted by the Ministry of Forestry and Environment. Next, I think by sharing about the some of our activities in our in our institution, I think what we are just want to summarize. Sorry. I think is that the use of satellite-based observations is quite useful and beneficial for addressing sustainable development goals, as well as the climate change mitigation. Of course, in doing that, we have a very intensive collaboration with various institutions at the national level, local level, as well as at international collaborations. And we also invite all researchers from all institutions in universities and international organizations to be part of our research activities or program to improve the use, to improve and to promote the use of space-based technology and application in addressing sustainable development goals and climate change mitigation. I think with that, I would like to end my presentations. Thank you very much for your kind attention.
Thank you very much for Professor Erna for the sharing. in perspective from LAPAN, BRIN. But before we close our morning sessions, I would like to invite everyone to join the photo sessions. So please, I would like to appreciate if you can turn on your camera to take the pictures together. So for today, we will help by Dr. Maya, if you are ready.
Yes, I'm ready.
Okay, so if everyone is ready, I think you have to stand by with the smiles again, because we have 8 pages right now. So for the first page first, let me count on 3, 2, 1.
Okay, wait a moment. Okay, next.
Okay. Next for the second page, 3, 2, 1.
Okay, next.
Okay, for the third page, 3, 2, and 1.
Okay, wait a moment, please. Okay, we can move to the fourth
Okay.
slide.
Okay, and next for the fourth, 3, 2, and 1.
Okay, wait a minute. Okay, move
Okay,
to the
great.
fifth.
Move the fifth, 3, 2, and 1.
Okay, wait a moment, please. Okay, for the sixth.
Okay, next for the sixth, 3, 2, and 1.
Okay, move to the seventh.
Great, for the seventh, 3, 2, and 1.
Okay, we will have the last slide.
For the last slide, last page, 3, 2, and 1.
Okay, thank you.
Okay, thank you very much, Dr. Maya, for helping us. And thank you for everyone here. Okay, so great. Now we will continue with the parallel sessions for the presentation from the invited speakers and also from the all presenters. So I would like to just remind everyone that we still have the same breakout rooms as we had yesterday. So we have 4 breakout rooms, namely by PS1 for the biomass conversion, PS2 with the bio-based smart material, PS3 for the forest environment, and PS4 for the hybrid topic of forest and environment, enhancing mitigation for climate change, radar and atmospheric science, and socioeconomy and in SDGs. So I would like to guide you how to join the next sessions. So if you can click the options of breakout rooms in the below of your Zoom meeting screen. And I think, okay, so sorry, it's namely by PS5 until PS8. So if you click the breakout rooms options, there will be another options pop up into your screen. And if you scroll down, there are 4 options. And if you see the join options in the right side of the breakout rooms name, you can click the join options to join.
Hello, everyone. I think we can start now. Okay, is my voice audible for you?
Yes.
Okay, thank you.
Okay, clear.
Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. Welcome to the parallel session number 6. Assalamualaikum warahmatullahi wabarakatuh. My name is Yudi. I'll be here as the host for the next couple hours today to run this parallel session about the bio-based smart material. And Mrs. Vida Bonar will also be here with me as the co-host. With a great pleasure, I welcome you to this event. Before we start this session, I would like to remind you that we would love to deliver an interactive session between you and the speakers. And for the presenters, we invite you to turn on your camera once we start introducing you, playing your camera, playing your video presentation, and beginning the Q&A session. And for the participants, we also encourage you to do so. However, if you are shy to turn on your camera, you may use the raise hand button on your screen to deliver your question, because we will not be using the chat room during the Q&A session. And for the best audio quality, we recommend you to use any listening devices. And for your information, this first Icon-Lig and 10th ISSH Symposium can also be accessed through our official YouTube channel. So you may stream it live from your phone, PC, tablet, and laptop. And the attendance form will be distributed throughout this session, so please fill it up whenever you can. Okay, now let's start our session by inviting our first distinguished speaker, Professor Kenji Umemura. So Umemura Sensei is a professor at the Research Institute for Sustainable Humanosphere at Kyoto University, Japan. He is the head of Laboratory of Sustainable Materials, and his specialties are development of wood adhesives, wood-based materials, and also the durability of the wood adhesive. His current interest is to develop new wood adhesion technology that do not depend on fossil resources. So I think we have Professor Umemura here. How are you, sir?
Yeah, I'm here.
Oh yeah.
Thank you very
How
much
are you?
yeah,
Thank
fine.
you.
Thank you. Thank you
Thank
very
you
much
for
kind introduction.
Okay, thank you, sir. Thank you for joining us today live, and we are about to play your video presentation. And for the IT staff, please help us to play video number 4A. Thank you.
Thank you very much for a kind introduction. I am Kenji Umemura, the professor of the Research Institute for Sustainable Humanosphere, Kyoto University. So first of all, it is my great pleasure to have the opportunity to talk entitled Potential of Sustainable Wood-Based Panels Using Agriculture Waste. This is global trend in wood removal from 1961 to 2019. So this is the round wood, and this is wood fuels, and this is industrial round wood. And the harvested wood, meaning the round wood, is being used in two ways. The one is the wood fuels, and the other one is industrial round wood. And in 1961 here, the production of the round wood is about 2.5 billion cubic meters. But in the 2090 here, the production is 3.9 billion cubic meters. So the production of round wood increased 1.6 times over 58 years. And the total volume of the industrial round wood is almost equal to that of the wood fuels like this. This means that the utilization of wood consists of the 50% of wood fuels and 50% of industrial round wood in recent years. And now the production of wood-based panel is added in this figure. It looks like this. This is the wood-based panels. So the production of wood-based panel increased gradually like this, and 9.0% of round wood is used for wood-based panels, and 70.7% of industrial round wood is used for wood-based panels. And the wood-based panels include the plywood, particle board, and fiberboard. So the next I would like to show you the details data. This is the wood-based panel production from 1961 to 2019. So as you can see that so this is the wood-based panels, and this is the particle board and the fiber board and the plywood. In the 1961 here, the production of wood-based panel is 25 million cubic meters. But now in 2019 here, the production is 358 million cubic meters. And the production of the particle board, including OSB, account for the 37%, and the fiberboard account for 33%, and the plywood is 30%. And considering the global population growth and the economic development, the production of a wood-based panel is expected to increase in the future. Basically, the wood-based panel consists of the wood element and adhesive. Therefore, when we develop the sustainable wood-based panels, so we have to think about the sustainability of the resources of the wood element and adhesive. So this means that the sustainability and the renewability of raw material are very important. So the first I'd like to think about the wood element. This is the change of the global forest area from 1990 to 2020. The forest area declined gradually like this, and 178 million hectares have been lost. The degraded area is equivalent to 4.7 times of the land area of Japan. And the rate of forest loss slow in recent years compared to the 1990 to 2000. So this is due to the forest preservation and the increase of plantation forest. But forest area is expected to continue to decrease concerning the deforestation and climate change. This is the change of growing stock in global forest from 1990 to 2020. So small decline was observed from 1990 to 2010. From 2010 to 2020, slight increase was observed. The total growing stock in 2020 is 556.5 billion cubic meters. The change of growing stock is less than 1% over the last 30 years. So this means that the global wood resources are almost constant in recent years. As you know, the forests provide a multi-function, meaning their biodiversity conservation function, global environmental preservation function, soil conservation, sediment disaster prevention function, water source research function, comfortable environment forming function, health and regulation function, cultural function, and material production function. The decrease in the forest area means there are loss of these functions. So the forest preservation will become more important in the future. Considering the situation, we need to think the utilization of unutilized lignocellulose resources as raw materials for wood-based panels. This is the global cereals production from 1961 to 2019. So as you can see that the production increased linearly like this. And considering the population growth and the economic development, the production will increase in the future. And the cereals contain the wheat, rice, corn, sorghum, and so on. And those cereals generate the agricultural waste, such as the stalk, straw, and bagasse. But recently, the open burning of these wastes is prohibited due to air pollution. So we have to deal with these wastes. To summarize these things, the production of wood-based panel will increase in the future. This reason is due to the population growth and economic development. But forest area will continue to decrease due to deforestation. Therefore, we need to investigate the alternative raw materials for wood-based panels. On the other hand, the cereals production will increase. With this, these waste will also increase. But open burning is prohibited concerning the climate change. Therefore, we need to investigate the utilization of agricultural waste. So, the utilization of agricultural waste as raw material for wood-based panels should be investigated. So next, I'd like to think about the adhesive. The adhesives are indispensable to wood-based panels. And basically, the adhesive is synthetic resin adhesive. For example, the polymer-based adhesive, PMDI, epoxy resin adhesive, polyurethane adhesive, water-based polymer isocyanate adhesive, and vinyl acetate resin adhesives. But this is the raw material of synthetic resin adhesive. So this is raw material of adhesive, this is hydrocarbon, this is resources. And here, as you can see that there are many raw material. For example, here the polyvinyl alcohol and vinyl acetate, styrene, phenol, acrylic acid, and MMA, bisphenol A, epichlorohydrin, and so on. And these chemicals are derived from ethylenes. And here, chemicals are derived from propylenes. Here from the butan-butagen cut, and here from the aromatic compound. And these hydrocarbons are derived from naphtha. In case of the formaldehyde here, is from natural gas. And naphtha and natural gas are fossil resources. So, basically, the synthetic resin adhesives are derived from fossil resources. So, considering concern about the future global environment and the potential shortage of fossil resources, it is desirable to reduce the consumption of synthetic resin adhesive. So, we need to replace the synthetic resin adhesive with bio-based adhesive or new adhesion technology independent of fossil resources as much as possible. Our laboratory investigates the development of wood-based panels using agricultural waste and new adhesion technology independent on fossil resources. So now I'd like to introduce the development of particle board using sorghum bagasse and citric acid adhesive, and the binderless particle board using oil palm trunk and ammonium dihydrogen phosphate. The sweet sorghum has planted in the large area as a multi-purpose plant for food and chemical agent. But a large amount of bagasse is generated as a waste. Conventionally, the bagasse is used as silage, but this utilization is a short-term carbon stock. So we investigate the possibility of the bagasse utilization for raw material or particle board. And citric acid exists lemon and limes, and it is used in many food and soft drinks. And citric acid is the organic carboxylic acid containing the 3-carboxyl group like this. And it is white crystalline powders and water soluble and weak organic acid. And citric acid is commercially produced by fermentation of glucose. So the citric acid is basically derived from bioresources. And recently, we found that citric acid can be used as a wood adhesive. So this is the manufacturing of particle board using sweet sorghum bagasse and citric acid. So first, we prepared the citric acid water solution as adhesive, and this solution was spread onto the sorghum bagasse particles, and after making the mat was hot pressed. Then we obtained the particle board using sorghum bagasse and citric acid. Figure 1 shows the effect of the citric acid content on the bending property of particle board. So this is the citric acid content, and this is MOR, and this is MOE. So as you can see that the bending property increase with increasing the citric acid content. And in case of the 20 weight percent of the citric acid content, the MOR was the 21.8 megapascal. So this value was satisfied to the JIS 80 type standard. And figure 2 shows the effect of citric acid content on the thickness swelling of the particle board. So this is the citric acid content, and this is the thickness swelling, and this is water absorption. So as you can see that thickness swelling decreases gradually with increasing the citric acid content. And in 28% of the citric acid content here, so this value was satisfied with the JIS 80 type standard. And this is the termite and decay resistance of the particle board bonded with the citric acid, and also the PF and the PMDI as a control. And here this is termite resistance, and this is termite mortality. The value was 42.8.
Recording in progress.
Excuse me, dear IT, could you please assign me for the break room? Thank you.
Waste and new adhesion technology independent on fossil resources. So now I'd like to introduce the development of particle board using sorghum bagasse and citric acid adhesive, and the binderless particle board using oil palm trunk and ammonium dihydrogen phosphate. The sweet sorghum has planted in the large area as a multi-purpose plant for food and chemical agent. But a large amount of bagasse is generated as a waste. Conventionally, the bagasse is used as silage, but this utilization is a short-term carbon stock. So we investigate the possibility of the bagasse utilization for raw material or particle board. And citric acid exists lemon and limes, and it is used in many food and soft drinks. And citric acid is the organic carboxylic acid containing the 3 carboxyl group like this. And it is white crystalline powders and water soluble and weak organic acid. And citric acid is commercially produced by fermentation of glucose. So the citric acid is basically derived from bioresources. And recently, we found that citric acid can be used as a wood adhesive. So this is the manufacturing of particle board using sweet sorghum bagasse and citric acid. So first, we prepared the citric acid water solution as adhesive. And this solution was spread onto the sorghum bagasse particles. And after making the mat was hot pressed. Then we obtained the particle board using sorghum bagasse and citric acid. Figure 1 shows the effect of the citric acid content on the bending property of particle board. So this is the citric acid content, and this is MOR, and this is MOE. So as you can see that the bending property increase with increasing the citric acid content. And in case of the 20 weight% of the citric acid content, the MOR was the 21.8 megapascal. So this value was satisfied to the JIS 80 type standard. And figure 2 shows the effect of citric acid content on the thickness swelling of the particle board. So this is the citric acid content, and this is the thickness swelling, and this is water absorption. So as you can see that thickness swelling decreases gradually with increasing the citric acid content. And in 28% of the citric acid content here, so this value was satisfied with the JIS 80 type standard. And this is the termite and decay resistance of the particle board bonded with the citric acid, and also the PF and the PMDI as a control. And here this is termite resistance, and this is termite mortality. The value was 42.8%. So this value was similar to the board with a PF resin like this. And in mass loss here, the value was 5.9%. So this value was similar to that of the board with PMDI like this. In the decay resistance here, in the brown rot fungus, this value was similar to the board with PF resin. And in white rot fungus here, so this value was lower than that of the board with PMDI. So based on the result obtained, it was clarified that the board bonded with citric acid had good physical and mechanical property and good biological durability. This is the bonding mechanism of citric acid. So basically citric acid react with the hydroxyl group of the raw materials. And ester linkages between the citric acid and raw material brought adhesiveness, causing the good physical properties. And this is the chemical bonding between the citric acid and the raw materials. And next, I'd like to talk about the development of binderless particle board using oil palm trunk and ammonium dihydrogen phosphate. The oil palm tree area in the worldwide is 21.2 million hectares, and oil palm is replanted every 24 to 26 years, and a significant amount of oil palm trunk is generated. Generally, the inner part of oil palm trunk become a waste because of its insufficient properties such as low strength and low durability. So, we investigate the utilization of the inner part of OPT for raw material of particle board. And this is the ammonium dihydrogen phosphate, called it the ADP. This is the chemical structure, and this is the molecular weight, and this is the pH, and so on. And basically, the ADP is used for the agricultural fertilizer and fire retardant. And recently, we found that ADP can be used as a curing catalyst of sucrose-based adhesive. So, first we prepared the ADP water solutions, and this solution was spread onto the inner part of OPT particles, and after making the mat was hot pressed. Then we obtained the OPT binderless particle board using the ADP. This is the mechanical and physical property of the binderless particle board using ADP. Figure 1 shows the bending property, and the x-axis shows the ADP content, and this is MOR, and this is MOE. As you can see that here, this is without using ADP. In that case, MOR is about 5 megapascal and MOE about 1.6 gigapascal. But when we use the ADP, the bending property increased. And in case of 10 weight percent here, the MOR is about 9 megapascal and MOE is about 2.6 gigapascal. Therefore, the addition of ADP less than 10% contributed to improvement of the bending property of particle board. And figure 2 shows the water resistance of the binderless particle board, and the x-axis shows the ADP content. This is thickness swelling, and this is water absorption. As you can see that thickness swelling decreases gradually with increasing the ADP content. And in case of 10 weight percent here, so this thickness swelling was the less than 10%. So the particle board with the 10 weight percent addition of ADP had excellent dimensional stability. Why does the board performance improve by addition of ADP? OPT contains the water-soluble component such as saccharides. And these saccharides change to the water-insoluble component during pressing by adding ADP. As a result, the OPT binderless particle board would be good properties. This is the conclusion. Utilization of agricultural waste for raw material of wood-based panel need to be investigated due to deforestation and climate change. Considering the future of fossil resources, the development of new adhesion technology independent of fossil resources is required. And according to our research, there is the possibility that the sustainable wood-based panels using agricultural waste and new adhesion technology can be developed. With this, I conclude my presentation. Thank you very much for your kind attention. Terima kasih.
Thank you very much, Professor Umemura, for the insightful presentation. Please join me to give a round of applause to Professor Umemura. So I can make a short conclusion that it is urgent to reduce our dependence on oil-based resources and start to look at alternative sources such as bio-based material to fabricate useful tools to support our society. Okay, I think we can start the next session about the Q&A session. So for participants, if you have question, please raise your hand and turn on your camera. I still don't see some. Okay, Mr. Sudarmanto, please deliver your question.
Okay, good afternoon. Thank you, Sensei. Sorry. Thank you for your yes. I want to ask about how about management oil palm trunk. Thank you.
Basically, so we obtained the oil palm from the Indonesia, and actually, so the how to say, the colleague of the Indonesian researcher obtained the oil palm trunk, and they prepared the chip from the trunk, and so as say we got those particles. Is it okay?
Okay, yes. Thank you, Sensei. Okay, enough. Thank you.
Thank you.
Pak Yudi, can I ask question?
Sorry.
Yeah.
Oh yeah, sorry, I was still muted. Yeah. Yes,
Okay.
you can ask.
Thank you very much, Sensei, for your interesting presentation. I would like to ask about the particle board from oil palm trunk and ADP. We know that the particle, the trunk contains many, what you call it, vascular bundle.
Yes.
And mixed with a kind of carbohydrate. So when you mix this with ADB, which one is the most influence the properties of the particle board?
Yeah.
Thank you.
Yeah, yes. Though as you know, the oil palm trunk have the many vascular bundles, and hemicellulose content is very high. That's why. So when we use the synthetic resin adhesive, the bondability sometimes very low. So that is a very, the serious problem when using the oil palm trunk. But so when, the ADP is the catalyst of the saccharide, especially the sucrose. And is it okay? Can you hear me?
Yes.
Oh, okay.
Here.
Yeah. And ADP is the catalyst of the saccharide. So this means the sucrose change to the water insoluble substances under the heating and the existence of ADP. So this means that those saccharides change to the insoluble component under the when manufacturing the particle board. So those saccharides act as the adhesive. This means this method is like binderless particle board.
Okay. Thank you, Sensei.
Yeah, you're welcome.
All right, thank you. I think we still have one more chance for one question, please. Okay, Mr. Sasa, please deliver your question.
Thank you very much. Good afternoon. So I would like to ask to Umar Sensei that the use of natural materials for the manufacture of adhesive is indeed in a lot of research, but maybe until now it's a limited commercialization on the use of natural material for the adhesive. Maybe Sensei can, based on Sensei's opinion or observation, when the natural material can use commercialize in the industry, maybe 5 or 10 years later. Thank you.
Yeah, at least the considering the fossil resources, so we need to have to use the those natural substances as a raw material of adhesive. But how to say, the uniformity, and when we think about the productivity or you as like industrialization of the bio-based adhesive, the how to say, the uniformity and the amount of the substances is very important. That's why, so I think we have to solve the many problem when using the those natural substances as a raw material of adhesive. But we have to use that. That is my opinion.
Thank you very much.
Yeah. Oh, I cannot hear.
Oh yeah, sorry. Okay, I think we can start moving to the next speaker. Professor Umamura, thank you very much for your contribution today.
Yeah, thank you very much.
Okay, terima kasih. Okay, for the next invited speaker, we have Dr. Keiji Koda. Keiji Sensei earned his bachelor, master's, and doctoral degree from the University of Tokyo in the research on pulp and bleaching. And after getting his PhD, Koda Sensei started his career as an assistant professor at Hokkaido University in 2000. And he is working in wood chemistry and its application for utilization of plant-based materials. Okay, we also have Dr. Koda here with us. Hello, sir. How are you?
Yeah, thank you for having me.
Thank you for your coming here. And for IT team, please help us to play the video number 4B. Thank you.
Okay, thank you for inviting me today. I'm a speaker, Keiichi Koda, Hokkaido University, Japan. Today, I'm going to talk about development of lignin-based biopolymers for sustainable use of woody biomass. This is the outline of this presentation. Firstly, I'll begin slowly with a very basic but important aspect for utilization of biomass resources. Secondly, I have to mention the significance of chemical conversion and modification of woody biomass, especially lignin. Thirdly, I'll mention some previous research work that deals with lignin-based polymer as a functional materials. And finally, I'm going to talk about lignin-based some functional polymers developed by our research group. Okay, let's move on to the first topic. There are various forms of resources on our planet Earth. Fossil resources, mineral resources, nuclear energy resources, natural energy resources, and of course, biomass resources. And they are divided into mainly two categories. First, as an energy source, and second, as a source of material. And of course, you have to remember these resources are also divided into renewable resources. And if you look at it, the important thing is biomass resources meets all three categories. Use of biomass as energy and as material are both important, but normally fuel is very cheap. So material use should come first. And once used as high value-added products, biomass-based material should be recycled like a cascade from higher place to lower place. So, what about the utilization of lignin? Lignin has a very complicated structure and it looks very difficult to use it for specific purpose. And we also have to think about the utilization of technical lignin. Huge amount of technical lignin, especially craft lignin, is produced all over the world day by day. And it is mostly recycled as energy. That is a very important process, but at the same time, we have to establish some methods to utilize it as value-added material. Then we are coming to the next topic. This is a concept of biorefining process. There are two major pathways. Firstly, woody biomass are converted into low molecular mass compounds that are often called platform compounds by depolymerization. And then they are reorganized to make chemicals and plastics. And as a second pathway, woody biomass are chemically modified to make chemicals and plastics, that is, high molar mass compounds. In the case of lignin, the first pathway is described as follows. Lignin is first depolymerized to obtain lower mass oligomers or monomers. They are mixtures. Then, after some steps like purification and reorganization, you can obtain lignin-based polymers. The second pathway is described like this way. So lignin is modified to obtain chemically modified lignin polymers. And if this is a final product and functional enough, it's okay. But if you need some other polymers with higher molar mass polymers, you need further rearrangement. So in summary, we have two major pathways to utilize technical lignin. First, depolymerization, then you can obtain polymer. The second, you modify the lignin, then you obtain polymer. These two pathways have advantages and disadvantages. In terms of yield, the second pathway is better because you can utilize most of the lignin feedstock. But in terms of molecular design, the first pathway is better because you can control the quality of the resulting polymer by choosing the low molecular mass compound. Now I'll show you some examples for two pathways. Lignin is often selected as a platform compound from lignin. In this research work, vanillin was converted to its derivative, and this derivative is further reorganized to a new polymer, in this case, polyester. And another example was from Japanese researcher. They used some kind of bacterial strain that can convert lignin into PDC, this compound, by means of vanillin and its related compounds. And then PDC was further reorganized to a new polymer, including epoxy resin that is known as a strong adhesive. These two research works are typical examples using the first pathway strategy. Next, I'll show you some examples of the second pathway strategy. It is typically seen in our research group. Technically, Professor Uraki and his co-workers, including me, have developed this kind of PEG lignin. Technical lignins are used as a base polymer. In our earlier studies, we modified technical lignins using these kind of epoxy compounds. The resulting polymer are soluble both in water and in organic solvent like a detergent. This phenomenon is called amphipathy. PEG lignin can be used for some purposes. Here, I'll show you an application as a cement dispersant. See what will happen next. And you have to remember, we just use exactly the same amount of water, but you can see our cement dispersant can help to expand the cement effectively. Next, we developed another method to make PEG lignin directly from wood. It's like a pulping process, and the resulting PEG lignin showed high reactivity and high thermal mobility. Easily, it can melt upon heating. Next, we try to fabricate polyester. In this process, we use this PEG lignin as a polyol component. On the other hand, this terephthalic dichloride, this is acid chloride and very strong reagent, was used as a polycarboxylic acid component. And at the beginning, we thought it was very easy, but resulting polymer was too brittle and broken very easily. So we had to change our strategy. Secondly, we changed the reaction condition. We tried to fabricate polyester fiber by interfacial polycondensation reaction, but still we only obtained very, very weak fiber. Some years later, we finally succeeded in making polyester film that is a bit flexible, less brittle, but not flexible enough as a functional polyester film. Finally, we have developed another method to add polyethylene glycol as the third ingredient. And the resulting polyester film is not so strong, but it's very soft and expand like an elastomer. So we decided to apply it as a functional material for electronic devices. Finally, I can tell you how we applied this polyester film as a functional material. Before we proceed, I have to mention briefly what EDLC is. EDLC is an electronic device that can charge and discharge electricity very rapidly. It has high power density, while its capacity is very limited, so its energy density is also limited. And we thought we can improve this electrochemical property of EDLC by using lignin-based material. This is a schematic diagram of EDLC. EDLC is mainly composed of three parts or three components: electrode, electrolyte, and separator. And in the charging process, electrolytes are bound onto electrode that makes electric double layer. In the discharging process, electrolytes are released from the electrode, and we can use it repeatedly by repeating charging and discharging process like this. Talking about electrode, we had already succeeded in fabricating activated carbon fiber from lignin, and we proved it improved the specific capacitance significantly. So our next target was separator, and we used lignin-based polyester film that I introduced before. So we tried to fabricate separator material from lignin-based polyester film by melt polycondensation reaction. At first, we tried to make it with binary mixture. Binary means two components. And in this step, we used maleic anhydride instead of using maleic dichloride. So at first, we used a binary system to fabricate lignin polyester, but this didn't give any good result. And next, we used a ternary system, meaning we used three components, and this gave good result. And this is the isolation process, but because I explained before, I can skip this one. And this is also, firstly, by binary system, we made a relatively flexible film, depending on the condition. This is a typical stress and strain curve for our binary polyester film. And this shows our film had moderate mechanical strength with a little bit of flexibility. This slide shows how to assemble EDLC. Firstly, we used the binary polyester film as a separator component. In a separate experiment, we used cellulose paper as a reference. And we used activated carbon-based electrode. And also, we used organic electrolyte that is composed of ammonium salt. After EDLC was assembled, its electrochemical properties were evaluated. The area of the cyclic voltammetry gives you information on the capacitance. In the meanwhile, the Nyquist plot gives you two kinds of resistance. Cyclic voltammetry showed that EDLC using binary polyester film gave almost a linear line, but not a rectangular area like cellulosic paper. And we found the reason by microscopic analysis. Cellulosic paper have a lot of porous structure, but our binary polyester film did not. So we thought we have to make porous films. This time we used sodium chloride powder during mixing process to make a porous structure on purpose. And EDLC with porous binary polyester film gave a much better result compared to the non-porous binary film. But if you compare it with cellulosic paper that is commercially available, the result was not so satisfactory. And we thought it was a contact problem. So next, we had to make more flexible film. Now we've come to the ternary polyester film that was successful. The ternary polyester films were made up of three major components: PEG lignin and another polyethylene glycol as polyol components, and maleic anhydride as polycarboxylic acid component. And as I showed you before, the mechanical properties of the ternary polyester film were not so good compared with that of binary polyester film. But we found one condition that gives very soft and flexible ternary polyester film. And we thought it can solve the contact problem of the EDLC assembly when we used binary polyester film as a separator. The electrochemical properties of the EDLC assembled with non-porous ternary film were even better than those with binary porous polyester film. And they were almost comparable to those with cellulosic paper as a reference. And finally, we fabricated porous ternary film, and it gave even better result compared with the cellulosic paper. But we are not sure why this resistance is not improved for the time being. Now we've come to a conclusion that may give you an insight in lignin utilization. Please see our publication if you want to know more details. And I have 4 more slides left, and I'd like to talk about further development after my research work. One of our student, Tyler, he has developed a new type of polyester film that was reinforced by tempo oxidized cellulose nanofiber. And it shows good mechanical property as well as its flexibility. Another PhD student, Pakan, she developed a carbon black embedded electrode. You can see it on the right side. Also, she used ionic liquid electrolyte. In this case, combination of A and C, instead of using the conventional organic electrolytes B and C that I used. Finally, she assembled EDLC and obtained good electrochemical performances in terms of energy density as well as power density. As I showed you before, in general, EDLC that is shown in this blue area shows excellent power density, but its energy density has to be improved if compared with other types of batteries. In our research work for these 10 years, we have developed lignin-based EDLCs, and its maximum electrochemical performance have come all the way up here. And our adventure still continues. This is the end of my story, and thank you very much for listening, and thank you very much for having me over in this symposium.
Thank you very much, Koda-sensei. It was a very interesting presentation. So, presenter, participant, please join me to give round of applause to Koda-sensei.
Thank you very much. Oh, sorry about the lot of noises.
No problem. It's okay. Okay, so for a short summary from me, lignin is the second largest naturally occurring biopolymer on Earth, and its unfailing for its utilization will be very crucial in shaping our future. Okay, we will be coming to the next session, the Q&A session. So I will open 3 questions to you. So if you have questions, please raise your hand. Okay. We are still waiting.
Pak Yudi, can I ask a question?
Yeah. Yes, sure, sure.
Okay, thank you very much, Dr. Koda, for interesting presentation. Yeah, my name is Subiakto from RC Biomaterials. I am interested in the application of lignin for cement dispersion.
Mm-hmm.
Could you explain more how the mechanism reaction between lignin and cement? So the when we use wood, and then the cement will be hardened fast. But if you use lignin, and then maybe the dispersion is very longer. So could you explain the reaction or the mechanism?
Without figure, it's a little bit difficult, but okay, I'll try hard. So the keyword is amphipacity that I mentioned in the video stuff, right? So it's soluble in water and solvent. So it has relative, what I say, hydrophobicity and hydrophilicity, right? And in that case, maybe it has some good electrical charge environment. So that means it has a good data potential or something like that. So I think that's something to do with excellent performance as a cement dispersant. That's one explanation.
Okay, thank you. Thank you very much.
But in detail, I don't know very much. Honestly.
A paper on this topic or publication?
Yeah, it was published in 2013.
Oh.
Yeah, so you can see it.
Okay, thank you very much.
Okay, thank you.
All right. Do we have another question?
I'm sorry, my name is Benny. My one question.
Yes, please, sure. Go ahead.
Thank you so much, Mr. Kechi. I have a story. I mean, I has graduate from physics faculty or prodi kalau Indonesia. I have research S1 degree for limestone in cement. I don't know what is relation with your presentation, but I need to know, have you tried to stress and strain in lignin composite of your research for another application? I mean, maybe architect, maybe, or anything. I don't know. Have you tried, Mr. Kechi? Thank you so much.
Oh, maybe I didn't catch you very well. So you mentioned the stress and strain test for some application, right?
Yes.
Oh. So for the I mean the components of electrochemical devices, we did it, but for other purposes we didn't. But maybe for the future work, I'm planning to do that, like Memura Sensei's work or something like that. Some application like adhesives or wood molding with adhesive or something like that. Yeah, it's just I'm thinking of. Okay.
It's specific. You done what for?
What for?
Yeah. You have done, but what for specific purpose for post specific?
I don't understand your point. What do you mean for specific purpose?
Specific main for maybe for architect. I mean architect. I like architect. I mean architect. I like architect. So maybe you can feel. Maybe you can tell in architect main purpose.
Sorry, I don't follow you.
I'm sorry. Thank you so much. Nice to meet you. Thanks.
Thank you.
Okay. We have one more chance. If you have any question, please raise your hand. Okay, Mr. Romy, please go ahead.
Thank you for the time. For Sensei,
Yes.
I would like to asking about the application of your product epoxy from biobased. Yeah. If we compare with the fossil, the fossil one, is there differences like degradation time or something like that? Is it the exactly same between the epoxy generate from biobased and the fossil from the fossil, or there is differences between both of them? And is it possible to application for the for aeroplane or something, aircraft, like bonding or something in high temperature maybe, or it's different that you?
I
Thank
think
you.
it depends, but so I mentioned as I mentioned in the presentation, maybe that depends on the condition, because the lignin itself is essentially a polymer, right?
Yes.
If you modified it with epoxy resin, it gives some kind of high molecular mass polymer, right? But if you are thinking the so-called commercially available epoxy resin, it's a little bit different, because the commercially available epoxy resin is composed of the very low molar mass compound, like platform compound, or like that, right? Because it is industrially controlled, right?
Yes.
So it's not so easy to compare it, but I think it's comparable. So, but maybe in terms of cost, maybe we have to cost or some environmental impact. We have to think of how we have to make epoxy resin, because if you use the epoxy compound, that means maybe you have to use some fossil fuels, right?
Yes.
That's one point, because the same is true for the polyethylene glycol. Yeah, you can make polyethylene glycol from the natural resources, and some Japanese company actually is doing that, but normally it costs high, right? So that's one problem we have to solve. So now I'm thinking of the using lignin and lignin derivative, and as a whole ingredient, not using a fossil fuel.
Oh, really? Okay.
So if you want to apply it to epoxy resin or polyurethane or some other resins, maybe we have to think the same problems. We have to face the same problem. Yeah.
So for I mean, is it the how to say the compatibility? Is it's more compatible to the natural fiber, like something because of it based on the natural fiber from the natural resource, or it exactly the same character, hydrophobe, like the general epoxy resin, yeah? Or maybe because of bio-based, so it's real better in compatibility with the natural fiber like that, or it's actually the same as the commercial epoxy.
I think it can control, but now I cannot predict. But if you modify the very surface, maybe it is possible. I think. You said the compatibility, right, with the natural polymer, yeah?
Yes.
So but the surface of the natural polymer is hydrophilic, right?
Yes,
But
yes.
in general, the surface of the plastic is hydrophobic, right?
Yes.
So in that case, we have to modify at least either width, right? Either surface.
Yes. Okay. Okay,
So
Sensei, thank you very much.
Thank you. My pleasure.
Okay, thank you. It was an interesting discussion, but due to the time constraint, I think if you still have questions, you can send Sensei email. We will provide you with the email address. Is it okay, Sensei Koda?
Yeah.
Okay,
If it's not enough, you can give me a lot more questions.
Okay. Thank you very much for joining us today. I think we should be moving on for the next speaker. Okay, we have Ms. Vida Barnard here. She will be delivering presentation about the physical chemical characteristics of citric acid cross-linking coated on old corrugated paper. So for Mr. ID team, please help us to play the video. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Today, I would like to present my work with my team entitled of Physico-Mechanical Characteristic of Citric Acid Cross-Linking Coated on Old Corrugated Paper. The food and beverage industry has become widely developed in the last decade in line with the changing of people's lifestyle. Especially in last 2 years, during pandemic situation, the F&B industry changed their business pathways by food delivery and takeaway system, which is correlated for the increasing on the food packaging demand. As we know, the commercial food packaging dominated with fossil-based plastics such as polyethylene, polypropylene, polyester, and so on, which are not biodegradable and accumulate in the environment if unwell managed. So, by this condition, paper-based food packaging is potential in case of eco-friendly state because it could be biodegradable and recyclable. Here, for this work, we utilize old corrugated board paper as the pulp source because we want to promote the sustainability and circular economy outlook, which guide to lengthen the utilization of materials. In the reality, commercial paper-based packaging commonly good with the plastics such as polypropylene and polyethylene to overcome the limitation on mechanical properties, low water and water vapor resistances. Is it fully biodegradable? No, it is not. It could be another serious environmental problem in the case of microplastics. Therefore, we're trying to find eco-friendly coating technology for packaging, and one of the most potential methods is polycarboxylic acid cross-linking. And one of the promising polycarboxylic acid is citric acid, which are cheaper and renewable than other PCA. The key factor of this process is the formation of the citric acid anhydride, then esterified with cellulose and promoting further cross-link. Both the formation of citric acid anhydride and esterification need some thermal initiation, hence activation temperature and time be the crucial factors to initiate the cross-linking process. It also should be noted that the activation energy of citric acid cross-linking is relatively high, therefore needs some catalyst to minimize the activation condition. In this work, we use a novel catalyst for citric acid cross-linking. It is sodium dihydrogen phosphate. It is a food additive, so it could be suitable and safe for food packaging. The mechanism of the catalyzation is the proton exchange between carbonyl group on citric acid and dihydrogen ion from SDP that could be initiated for citric acid anhydride formation as a key factor of the cross-linking process. So the aim of these research are first to study the effect of activation condition of cross-linking agent, including temperature and time, and the second one is to evaluate the effectivity of sodium dihydrogen phosphate as a catalyst on physico-mechanical properties of coated old corrugated paper. For the raw materials, we use only the corrugated and inner layer of the OCB as the pulp source, citric acid as a cross-linking agent, and sodium dihydrogen phosphate as a catalyst. First, the paper were cut into pieces, then immersed for 24 hours, and then disaggregation using water blender for 3 minutes. Pulp then mold in round paper molding and maintained in 150 grams square meter. After molding, the paper conditioned at room temperature for 3 days and then oven dried at 80 degrees Celsius for 6 hours. The conditioned paper was sprayed with citric acid in various concentrations in 5, 10, and 15% by weight. And for the catalyst analysis, the citric acid solution was added with the SDP in 5 grams per meter square. The papers then activated in various temperature and time. And after activation, the papers were conditioned for 5 days, then oven dried at 60 degrees Celsius for 8 hours to maintain the moisture content before testing. The physical characterization, including moisture content, is referred to as SNI 638-2014, water absorption referred to as SNI 0499-2008, and the water vapor transmission rate referred to ISTM E95-1995. The mechanical properties, we are using a UTM with the load cell 5 kN, and the method referred to SNI 1924-2016 with a constant rate in 20 mm per second. The chemical compound analysis using FTAR, UATR. The samples were immersed in 0.1 molar sodium hydroxide to remove the untreated polycarboxylic acid. This is the result of this work. To analyze the effect of activation temperature, the activation time will determined in 5 minutes, and then the activation temperature will vary from 150, 170, and 190 degrees Celsius. We can see over here, the appearance of the paper tend to be darker as the increasing of temperature, but in slightly different, so equally similar at glance. And for the moisture content of the paper, in the case of the same citric acid concentration, activation temperature enhancement decreased the moisture content. And moisture content also increased as rising concentration in the case of the same activation temperature. This may be because of the excessive carboxyl group of citric acid that have not crossing yet in 5 minutes, so could easily bond with the hydroxyl groups of water vapor. The water absorption and water vapor penetration of treated paper are decreasing as the temperature increases at the same citric acid concentration. Treated paper processed at 190 degrees Celsius has the lowest water absorption in 423 point something gram per meter square for 5%, and while for water vapor penetration in 0.021 something gram per hour per meter square for 15%. These results show for the water absorption and water vapor penetration improvement in about 40.60% and 50%. Than untreated paper. The tensile strength and modulus of elasticity of treated paper increase as temperature increase, but overall the treated paper have lower mechanical properties than the untreated ones. This is the effect of the activation time. According to the optimum activation temperature before, in this term we determine the temperature at 190 degrees Celsius with the activation time will vary in 3, 5, and 7 minutes. The appearance of the paper, as we can see over here, tend to be darker as the addition of the activation time up to 7 minutes. And for the physical properties, lower activation time produces for lower moisture content, water absorption, and water vapor penetration. A similar result has occurred for physical properties that the best value are in 7 minutes and 10% of citric acid concentration. The moisture content is about 2.46%. Water absorption is 302 point something gram per meter square, and water vapor penetration is 0.015 gram per hour per meter square. Water absorption drops up to 57.6%, while water vapor penetration is up to 75% than those of untreated paper that attribute to the better cross-linking process on the paper surface. The tensile strength and modulus of elasticity of the treated papers improve as rising of activation time, especially for 5% and 10%, while relatively drop for 15%. This result still remains under the untreated papers. This is the effect of the catalyst. In comparison to the catalyst effectivity, the SDP was added to the 10% of citric acid solution. The addition of SDP affects the moisture content, water absorption, and water vapor penetration improvement as resting time up to 7 minutes and temperature at 170 degrees Celsius. We can see over here for all physical properties result in lower value than the paper without catalyst in the same activation time up to 7 minutes and temperature up to 170 degrees Celsius. The effectivity of temperature and time perform for the effectivity of the catalyst. For instance, in the same temperature, 150 degrees Celsius, the water absorption of treated paper without catalyst in 7 minutes result in slightly difference of about 1 up to 9% compared to paper with catalyst in 3 up to 5 minutes. This result seems to indicate that the catalyst has no significant effect on cross-linking effectivity. For the mechanical properties, the tensile strength value increased as the temperature level up into 190 degrees Celsius in all activation time. This result improved even slightly higher in 3% than untreated paper. But overall, the addition of SDP improved the tensile strength in all temperature and time compared to the treated paper without catalyst. This is the chemical component analysis of the paper by FTIR spectrogram. It should be noted that the free carboxyl groups and cross-linked carboxyl content may identify at the same spectra in 1730. Therefore, it needs saponification treatment by washing the papers using sodium hydroxide to eliminate the untreated polycarboxylic acid. The free carboxylic acid after treatment perform into carboxylate ions, which strongly appears in spectra 1589. The spectra of carboxylate groups are clearly identified after washing for all citric acid concentration and the paper with the catalyst, but it doesn't identify in the untreated paper and paper without treatment. Strong spectra in 1730 indicate for the cross-linked carboxyl group. The intensity of that band decreased in 5% of concentration, while quite broad in 1580, which corresponds to more unreacted citric acid is conferred. A technical approach for indicating the degree of cross-linking could perform by intensity ratio between 1730 to 1589 band. The ratio for 5% is 0.41, 10% is 2.3, and 15% is 1.3, while by addition of catalyst, the ratio is about 1.35. This result emphasizes that the higher ratio degree of cross-linking provides better physico-mechanical properties. From the previous result, there could be concluded in some points. For the first one is the activation temperature and time remarkably affect for the physical and mechanical properties of the papers. Activation temperature at the 190 degrees Celsius and time in 7 minutes produce the best physical-mechanical properties of coated paper than others. And the second one is the sodium dihydrogen phosphate as a catalyst has no significant effect on the effectivity of cross-linking process for limiting the water penetration, but it results in better mechanical properties. According to the previous conclusion, further study is considerably needed to improve the mechanical properties as well as the effectivity of the cross-linking process with and without catalyst. This is the end of my presentation. Thank you for your kind attention.
Okay, thank you, Mrs. Widabornar. It was an interesting presentation. So we are coming to the Q&A session. So I think I will give you only one opportunity for questions. Sorry about that. So please raise your hand if you have a question. Okay. Okay, Sir Romy, please go ahead. Yes, Mr. Romy.
Sorry,
Oh,
I don't raise my hand.
Oh,
Sorry.
okay, sorry. Oh, you were on chat. Sorry. Okay. Okay. I think we don't have.
Okay.
Okay. Okay, sir.
Okay.
So please go
Maybe
ahead. Okay.
no question, and I would like to ask it. So, for the presenter, so I'm sorry. With the presenter name? I'm sorry, Miss. The name of I want to ask. So
Miss
you
Mida.
want to Miss Mida?
This is Miss
So
Mida, yes.
so Miss Mida, do you want to? So your work is to improve the hydrophobic about water absorption, to avoid water absorption of the paper. Yeah, you make a paper to, how to say, to avoid the water absorption is by treatment. Yeah, make a chemical treatment with citric acid. Is it correct?
Yes, Pak Romi.
And the, how to say, oh, so for as citric acid as catalyst, yeah. So hydrogen. Why you decided to use this kind of catalyst? Is it a previous study or something? But because as I know, there is many, how to say, treatment, yeah, like acetylation or something like that, yeah, to improve the hydrophobic character of fibers, yeah, like acetylation, yeah, acetylation. Why you choose this treatment, not the common treatment? Do you understand my? You get the
Yes, I can catch your question, Mr. Romi.
Okay. Thank you, Miss.
May I answer this directly, Mr. Yudi?
Yes, please.
Thank you, Mr. Romi, for the question. Okay. Do you ask for a question about the why I'm using citric acid? The first, because of citric acid is a polycarboxylic acid that's could be cross-linked with the cellulose, so it could be have a higher water resistance. So in the previous study also mentioned in many journals that the addition of the citric acid could be cross-linked and have ability to maintain the water absorption. So we use here citric acid because of the application for this paper. For the paper should be as a food packaging. So we decide to use citric acid because it eco-friendly agent for cross-linking. So and then the citric acid actually as a cross-linker, not a catalyst. We use another catalyst with sodium dihydrogen phosphate for cross-linking effectivity. Why we use the SDP? Because it's a food additive and good, suitable, and safe for the food packaging. Can you catch up for my answer, Mr. Romi?
Yes, I understand. So I also have a problem. I would like to, in my case, I want to, how to say, to increase my hydrophobic character of my resin, but I try to do the, how to say, using acetylation, but with acetic acid glacial, yeah, as catalyst, I think. But I don't have any, how to say, references. but so it's interesting to me to know how you did the experiment, yeah, to improve to decrease the hydrophilic character of the pepper. Yeah.
Maybe we can discuss privately.
Okay.
Before previous study, my previous study also use make a acetylation treatment for limiting the to increase the water in hydrophobicity.
Okay, it's
Okay,
nice.
thank you.
Maybe I can get by email or contact after this.
Okay, thank you.
Okay,
Okay.
Thank you.
Thank you. It was a nice discussion. I think we'll be moving on to the next speaker. So we have Tati Husniati. She will be talking about protein stability of indigenous Lactobacillus fermentum EN17.2 and Lactobacillus plantarum B110 at storage. So for the IT team, please help us to share video number 602. Thank you. I can't hear the voice, Mister. Could you please replay it? Mr. Jauhar?
Grow quickly, can grow on thick substrate, and easily increase in yield through regulation of fruit condition and genetic engineering, and are able to produce enzymes with extreme conditions. Lactic acid bacteria are safe microorganisms. Gentlemen, I would like to present our research result with the topic protein stability of Lactobacillus fermentum EN17.2 and Lactobacillus plantarum B110 indigenous at various storage time and temperature. Protease is a protein hydrolyzing enzyme with its hydrolysis produces peptide and amino acid as simple compound. Protease is one of the enzymes that has the best potential to be developed because it is considered quite good and can be used in various fields such as industry, food and non-food products that are traded around the world. Economically, protease from microorganisms more profitable because microorganisms grow quickly, can grow on thick substrate, and easily increase in yield through regulation of fruit condition and genetic engineering, and are able to produce enzymes with extreme conditions. Lactic acid bacteria are safe microorganisms because they are non-toxic and do not produce toxin. So they are known as generally recognized as safe-grade microorganisms that are not a risk to health. Even some types of bacteria are useful for health. To reduce the import of enzymes in Indonesia, which continue to increase every year, is a needed production of local enzymes from indigenous lactic acid bacteria as an alternative enzyme source. Based on the above, proteins producing lactic acid bacteria need to be examined so that its potential can be found, especially local bacteria. This study focused on the protein stability of Lactobacillus fermentum EN17.2 and Lactobacillus plantarum B110 indigenous at various storage temperature and time. The research method subculture bacteria by using MS root medium inoculated into liquid media, vortex, stored in incubator for 24 hours and temperature 35 degrees Celsius. For protease production by using casein and nutrient-proof medium, for pack incubated at 37 for 24 hours, centrifuge 15 minutes at 5 degrees Celsius and supernatant risk of time. Protease at storage temperature and time for 0, 7, 14, 20, and 23, and treat cold and freezing temperature. For protease activity assay, the formula, the protease activity unit per milliliter, the same as concentration tyrosine divided and R-tyrosine cross V divided P cross Q cross dilution factor. Protease relative activity, the formula, protease relative activity, the same as treatment activity unit per milliliter, divided highest activity unit per milliliter, cross 100%. Protease statistical test at various temperature and storage time, the data were analyzed statistically using ANOVA and Duncan test to determine whether there was a significant difference in the simple data. The research result, the activity of protease fermentum at freezing temperature at time storage of 0, 7, 14, 20, and 28 days did not show us any significant difference. For protease activity fermentum at UD, could show a significant difference with protease activity fermentum at 28 days. The relative activity of fermentum protease at cold temperature at storage time 7 to 28 days range from 53 up to 90%. The activity of plantarum at freezing and cold temperature at 0 of storage was not significantly different from the activity of L. plantarum protease unit at 28 days of storage. Table 1, unit activity and relative activity of L. fermentum protease at freezing and cold temperature at various storage time. This table shows that at freezing temperature for 0 day compared to 28 day, the value of protease activity did not significantly different. For cold temperature, storage time 0 day compared to 28 day, the value of protease activity significantly different. Protease activity at freezing temperature from fermentum was better than at cold temperature, and the protease relative activity for freezing temperature at 28 days 60%, but cold temperature 53%. In table 2, unit activity and relative activity of L. plantarum B110 protease at freezing and cold temperature at various storage time. In storage time 0 day at freezing temperature compared to 28 day, the value of protease activity significantly different. Also in cold temperature, storage time 0 day compared to 28 day, the protease activity also significantly different. Protease activity L. plantarum compared with protease activity L. fermentum before. The storage time at freezing temperature, protease activity L. fermentum was better than protease activity in L. plantarum. The protease activity at core temperature of food bacteria during storage time 728 degrees show no significant difference compared to the freezing temperature, while the protease activity of L-fermentum at core temperature at duration of storage show a significant difference compared to the freezing temperature. This difference was probably due to the degradation of substrate, especially protein by protease at core temperature less than at freezing temperature, so that protease activity at core temperature is higher than at freezing temperature. The protease activity was influenced by the substrate component, especially the protein content. The higher the protein content, the more protease activity increase up to the activity reach its optimum. Several factors that influence protease activity include substrate with its nutrient compound and temperature. So the conclusion, the protease stability of L-fermenting AN17-2 with a relative activity of 60.0.6% at frozen temperature for 28 days was not significantly different from G2T. On the contrary, the protease stability saw a significant difference at core temperature. The protease stability of L-plantarum B110 with a relative activity of 52.26% for 28 days at core temperature and with a relative activity of 50.51% at freezing temperature were significantly different from G2T. Based on the stability of protease, the protease stability of L-fermentum AN17-2 was better than that of L-plantarum B110. As a source of protease producing lactic acid bacteria, to use L-fermentum AN17-2 as protease source was recommended. And the author would like to thank the project of Biomaterials, Research Center for Biology, Deputy of Life Sciences, Indonesian Institute of Sciences for providing research fund, partial funding for publication fee from Japan Society for the Promotion of Sciences, JSPS, and Mrs. Desi Septiani, SSE, for her assistance in the laboratory. Thank you.
Okay, thank you very much, Bu Tati, for the nice presentation. So we are now coming to the Q&A session. So for the participant, if you have questions, please raise your hand. Oh. Mr. Robbie, are you? Do you have question?
Sorry, I don't have. Sorry,
Okay.
sorry.
I saw you raise your hand. Okay, no problem. So if you have question, please raise your hand and give your question. Okay. I think no question for now. So probably we should be moving on for the next speaker. So, okay. We have Mrs. Dian Burhani. She will be talking about preparation of hydrogel-based chitosan using citric acid and crosslinker for matrix drug delivery. So for the IT team, please help us to play the video number 603. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. First of all, allow me to thank to you that the time that you're giving to me. Second time, let me introduce myself and my team. My name is Arska Sabila Hanifah. My team were Dewi Sondari, Sandra Hermanto, and Ahyar Ahmad. On this occasion, I will present the journal that we have made. The title was Preparation of Hydrogel-based chitosan using citric acid as crosslinker and aldehyde cellulose from sugarcane trust, Saccharum officinarum for matrix drug delivery. The background of this research, because in Indonesia, especially at Java and Sumatra Island, sugarcane was a plant that was widely cultivated for commercial needed as a consumption sugar, which produced waste in the form of unused stem and leaves. Usually, producers of a consumption sugar using the unused stem and leaves to be a fertilizer. However, the previous research from Singh et al. In 2008 said that the sugarcane trash leaves contain much of cellulose and hemicellulose, and its statement were strengthened by Zurhamita and Mahyudi in 2012 that say the unused stem and leaf of sugarcane still contains approximately 37.65% of cellulose. Cellulose need more treatment to maximize the benefit, and one of them we are going to use the cellulose as ingredient of making hydrogel. K&L in 2018 said that the hydrogel from chitosan cellulose composite were reported have chelation driven by Schiff-based reaction, are incredibly porous materials that are capable of loading numerous potential therapeutic agents. The hydrogel was a three-dimensional network of hydrophilic polymer that have ability to swell and hold a large amount of water. The hydrogel can be used in agriculture, biomedical, and many more. The purpose of this research: first, we want to utilize the sugarcane trash, especially leaves, from a waste to be an hydrogel and its application as methods of drug delivery. The second one, we want to know the effect of differences concentrations from oxalic acid in cellulose isolation treatment on the characteristic of the resulting hydrogel. The materials that we use in this research: sugarcane trash we got from PG Raja Wali II from Subang, West Java, Indonesia. We use chitosan from Sigma aldrich. We use sodium hydroxide, hydrochloric acid, citric acid, oxalic acid, sodium periodate, hydrogen peroxide, acetic acid, methylene blue, and phosphate buffer saline for Merck without purification. We use distilled water in the whole process. The equipment that we use as delignification, we use a microwave reactor and autoclave. In synthesis form, we use hot plate, thermometer, vacuum, and we characterize using spectrophotometer, infrared, microbel reader, spectral nano UV vis, and shaker for characterize the hydrogel and application as methods of drug delivery. The method that we use in this research: first, sugarcane trash sample was washed 3 times in hot aqua dash. Then we delignificate using microwave reactor by oxalic acid solution that had a concentration 0.7% and 1.8% with the ratio of the sample and the solution is 1% in the temperature 180 degrees Celsius for 5 minutes. Then we neutralize with aqua dash and dry in the oven at temperature 60 degrees Celsius. We are going to delignification again using autoclave by solutions sodium hydroxide with the concentration 2%, and the ratio between sample and the solution is 1% at the temperature 121 degrees Celsius for 1 hour. Then we neutralize again with aqua dash and dry in the oven. Follow the delignification. To isolate the alpha cellulose, we use the bleaching method using peracetic acid. Peracetic acid will use the solution that contains hydrogen peroxide and acetic acid. Then we neutralize with aqua dash and follow the bleaching. We want to derive the cellulose that were made to make dialdehyde cellulose by oxidation using the sodium periodate that have a concentration 0.8%. by stirring it at the temperature 45 degrees Celsius for 1 hour in the dark condition. After that, we dry in the oven at 60 degrees Celsius, then characterize the dialdehyde cellulose using the spectrophotometer infrared. The dialdehyde cellulose we're going to make an hydrogel by adding the chitosan and citric acid. By stirring it to 500 rpm and at temperature 60 degrees Celsius for 90 minutes. And the solution were put in the Petri dish and dry in the oven for temperature 40 to 45 degrees Celsius. The result and the discussion. The utilize of lignocellulosic research from sugarcane trash to make derivative of cellulose as dialdehyde cellulose proven to be effective. To show the differences between the concentration of oxalic acid, we analyze the hollow cellulose content and alpha cellulose content. It shows that 0.7% of oxalic acid shows the optimum ones, because OP shows the higher hollow cellulose and alpha cellulose content than the MOP. MOP one were made by using the 1.8% of oxalic acid. The overlay of spectrum infrared from dialdehyde cellulose shows not so much difference between them. The peaks from 1644.47 and 1641.81 shows the carbonyl group from aldehyde. It shows that the DAC were proven to build, while the 1140.54 shows the bonds between carbon number 1 and carbon number 5, and it shows the beta 1.4 glycosidic bonds. The effect of using the different oxalic acid shows in swelling degree. The OCC sample that used the optimum of oxalic acid shows a great ability to swell that up to 3,567%, while the MSCC 440. Here the visual of the hydrogel that were made. This was the overlay spectrum infrared of the hydrogel. It shows that the board intensity of 3,374 peaks shows the groups of hydroxyl and amine group, while the 1,720 shows the corresponding to the carbonyl group from ester in citric acid. Their possible reaction was when the free hydroxyl group and amine group of chitosan was cross-linked with the hydroxyl group from ester in citric acid. However, the cross-linking in this reaction of the hydrogel was made by the two of reagents. The dialdehyde cellulose and chitosan made the shift-based reaction that shows the carbonyl group from dialdehyde and the amine group of chitosan were bonds and made an imine group. According to standard curve of methylene blue in two types of medium, it can be seen in here. The two types of medium represent our body solution. The drug loading and the encapsulation efficiency is directly proportional. The more drugs were encapsulated shows, the more also drugs were loaded. The medium show an impact that is not significantly drug loaded. The highest efficiency was the hydrogel with sample MACC. The efficiency encapsulation from MACC was 85.2%, and the drug loading was 23.1 milligram per gram in phosphate buffer saline medium. The drug loading means that 23.1 milligram of the drug were loaded per 1 gram of hydrogel, while the sample of OCC shows that 22.9 milligram per gram in phosphate buffer saline medium. The drug release rate is the percent value obtained from the ratio between the amount of drug released and the amount of drug that has been successfully encapsulated in an interval of time. The in vitro release of methylene blue as a drugs model were shown in this picture. In phosphate buffer saline medium, the hydrogel of MSCC for the first hour had a release rate of 12.34% and so on until it released 89.84%, while in hydrochloric medium that shows 89.80% release after 5 hours releasing. It means that 12.34% of the total drug loaded was successfully released into the medium, and so on until it released at 89.84%. However, the hydrogel OCC in phosphate buffer saline medium shows the release rate were 89.82%, and in hydrochloric medium shows 87.26% after 5 hours releasing. In conclusion, based on the research conducted, it can conclude that the MSCC and the OCC hydrogel from chitosandialdehyde cellulose and citric acid shows a potential carriers for drug delivery. The experimental shows that the MSCC hydrogel can swell up to 440% in water after 15 minutes, and the OCC hydrogel can swell up to 3,567%. Both sample hydrogel shows a great encapsulation efficiency, drug loading, and drug release in phosphate buffer saline medium. The gel can releasing optimum drugs for 5 hours.
Thank you for the presentation. So it was the presentation from Ms. Hanifah, not from Ms. Tian Burhani. So my bad, sir, I made a mistake. So, okay, we are coming to the Q&A session. So there is only one chance for you to deliver your question. So please raise your hand if you have a question to Ms. Hanifah. Okay. Okay, I have a question if you don't mind. Is your drug chemically attached to your hydrogel or just physically attached?
Thank you for the question. And I'm sorry because my connection was bad, so I can't turn on my camera.
Okay, no problem.
The drug were going to immerse in the hydrogel, but it's potentially as not a chemical bond because the releasing time of the drug carriers just for 5 hours release in the
Miss Hanifah? I can hear your voice. I think she is disconnected. Okay, I think we should be going to the next agenda, which is lunch break. Okay, ladies and gentlemen, we will be having our lunch break for about 25 minutes. So hopefully you will be ready at 1:25, which is 5 minutes before the session. So thank you very much for your attention. We'll be waiting for you for the next session at 1:30. Thank you.
Indonesia is a beautiful archipelago country with a tropical climate and an enormous natural resource. Forests and their biodiversity are the most valuable natural resources and the natural capital of Indonesia. The forest area in Indonesia continues to shrink. The accelerated population growth has caused forest exploitation in fulfilling the demand for wood raw materials, both legally and illegally. While this demand keeps increasing, the wood supply continues to decline. Wood is a raw material that is greatly useful and valuable for humanity. It is used for construction materials, furniture, handicrafts, firewood, and a variety of household uses. Founded in 2002, the Research Center for Biomaterials, Indonesian Institute of Sciences, has been conducting research in natural materials, such as wood and natural fibers. The center also focuses on developing processes, technology, and design to produce value-added products. The Modification and Engineering of Biomaterials Research Group focuses on characterizing and modifying lesser-value wood materials into more valuable products. This research group works closely with another research group called Biocomposites Engineering and EcoStructure. They've been working on engineering wood-based materials and natural fibers, such as bamboo, into functional composite materials. This research group also works on building material design and providing a technology package of an eco-friendly home, known as EcoHouse. All parts of the EcoHouse use eco-friendly composite materials. It also utilizes an architectural concept that conserves electrical energy. One of the research interests of the Biomass Process Technology and Bioremediation Research Group involves the utilization of lignocellulosic materials, such as non-wood natural fiber, and incorporating their conversion process to create bioenergy or bioethanol. Lignocellulosic materials can also be used as a medium for making enzymes that are used in bioremediation processes. These waste-degrading enzymes can be used to remove color and toxic materials present in textile waste. This research group is also developing derivative products such as wood adhesives made from natural latex. These adhesives do not produce emissions of harmful substances. They are friendly to human health and the environment. The Urban Agricultural Pest Management Research Group has focused their research on maintaining the quality of the wood commodity and protecting cellulose-based products from the attack of pests such as insects and fungi. By utilizing natural materials such as plant extracts and microorganisms, this research group has been developing eco-friendly urban and agricultural bioinsecticides and studying their biocontrol approaches through laboratory bioassays as well as behavioral and ecological studies. The research outcome is part of this group's efforts to tackle the process of biodeterioration that is caused either by wood-attacking insects or wood rot fungi. Through a series of chemical, biological, mechanical, and physical processes, natural materials can be transformed into biopolymers, bioactive compounds, conventional composite materials, advanced and ingenious materials, as well as other products that are eco-friendly. In addition to providing high economic value products, natural-based materials can also be converted into renewable fuels as substitutes for fossil fuels. Appointed as the Center of Excellence for Lignocellulose, the Research Center for Biomaterial also has an ISO IEC 9001-2008 certification for quality management systems. It also serves as an appointed urban agricultural pest testing laboratory authorized by the Pesticide Commission of the Indonesia Ministry of Agriculture. Since 1996, the Research Center for Biomaterials has been a satellite office for foreign cooperation between LIPI with Kyoto University, Japan. The center is also active in research programs in Asia, such as JSPS and SATREPS. In addition, the Research Center for Biomaterials has been cooperating with various research institutions, universities, and industry from home and abroad. The Research Center for Biomaterials continues to develop advanced materials and bioproducts through a series of processes in order to support a clean and healthy environment. The Research Center for Biomaterials, Indonesian Institute of Sciences, appointed as a Center of Excellence, continuously advances innovation in addressing global challenges.
Okay. Good afternoon, everyone. Welcome back to the break room 2 with the research interest in bio-based smart materials. Thank you very much for your staying with us still in this room. Hope all you have enjoyed your breaks and we can continue our session with a fresh body and mind. Okay, to maintain the interaction, please open your camera and turn off the audio during the session. For your information, for the session, we will divide into 2 groups for 3 presenters for each group. And I'm Mida Banar, and I will be the host for the first groups on the session. Okay, for the first presenters is Miss Dian Burhani. She earned her bachelor degree in Universitas Negeri Padang and master degree from Institut Teknologi Bandung. And she is working in Research Center for Chemistry since 2015, and she is interested on bioenergy and nanocellulose. Please, for IT, to play the presentation video of Miss Dian Burhani. Thank you. Mr. Jauhari, could you please relay the video?
Assalamualaikum warahmatullahi wabarakatuh. Good day, everyone. My name is Dian Burhani. I'm a researcher from Research Center for Biomaterials, Indonesian Institute of Science. First of all, I would like to say thank you to Icon-Lig, who has given me an opportunity to share my research regarding the potential of K-pop, cellulose nanofiber, chitosan aerogel as an oil absorbent. Okay, first let me share you my slides. So, oil spills, one of the major environmental issues in the marine ecosystem, have exposed severe risks to aquatic life and human health. Oil-contaminated water from accidents that might be happened during oil production, storage, and transportation needs urgent management. Therefore, developing robust and facile technology to remove the oil pollutant is inevitable. There have been many techniques to clean up the spilled oil, including physical, chemical, and biological. Physical methods such as booms and skimmers, which are commonly used to not remove oil from the sea surface effectively. Chemical methods involving complicated and expensive process, including dispersion, in situ burning, and solidification, often generating second waste after the oil removal. A biological approach with the use of microorganisms is considered effective. However, it is time-consuming and relies on many parameters, including pH, temperature, dissolved oxygen, and other factors. So natural absorbent materials have been drawn attentions from an environmental perspective due to the feasibility of absorbent collection, higher effective oil removal, and more cost efficient. The sorbent disposal is also easier and poses the least environmental hazard than synthetic absorbent. Among other natural absorbents, K-pop, a cellulosic fiber with a hollow structure consisting of main components such as cellulose, lignin, polysaccharide, and minor components including waxy coating. Cellulose is one of the most abundant and environmentally friendly polymers found in nature. Nanocellulose, the nanoscale version of cellulose, is classified into 3 types according to their isolation methods, including cellulose nanocrystals, cellulose nanofiber, and bacterial cellulose. The term aerogel is defined as lightweight and highly porous material resulting from the sublimation of liquid or solvent to air. With the low density, high porosity, and high specific surface area, aerogel is considered an ideal absorbent to absorb more oil and stay floated on water. CNF aerogels have raised attention owing to their excellent absorption performance, environmentally friendly, and sustainability. Therefore, it is crucial to select a suitable material with particular characteristic as an oil absorbent to improve the oil removal from water. Both Kapok and cellulose nanofiber aerogel has shown typical behavior as an excellent oil absorbent. Therefore, in this study, with that hypothesis, for the first time, we use Kapok fiber as substrate and cellulose nanofiber as the matrix and chitosan as filler, and fabricated an aerogel using a facile method by freeze drying. So for the materials, we use cellulose nanofiber, which was prepared by mechanical treatment using supermass colloider from oil palm empty fruit bunch from a previous study. Kapok was provided by Kapok.co from Japan. 100 mesh chitosan with the acetylation degree of 87.5% was diluted in acetic acid solution. For the preparation of aerogel, cellulose nanofiber and chitosan with the mass ratio of 1:3 and 1:5 was homogenized using ultra-2rex for 50 minutes. Kapok was blended into the mixture using a laboratory blender. The CNF chitosan Kapok mixture was placed in a Teflon mold, then frozen at -80 degrees Celsius for at least 8 hours, followed by freeze drying for 48 hours. So from this study, we obtained a slightly white, firm with a rough and uneven surface aerogels, which was shown in the slide. The Kapok fibers were still clearly visible since no solvent was used to dissolve the fiber. Next, we analyzed the chemical changes of the blending using FTIR and found that at the peaks of 1733 to 1732 inverse centimeter and 1241 inverse centimeter are associated with the presence of the carbonyl groups in the ester bonds. The CO stretching vibration are assumed to be related to the aliphatic aldehydes, esters, and ketones of Kapok wax, which was the characteristic of hemicellulose linkage. Significant differences were observed at the peaks of 1543 to 1538 inverse centimeter, which are assigned to the amino groups of chitosan in CNF chitosan aerogel and Kapok CNF chitosan aerogel, but were not found in CNF only aerogel, which indicating that the chemical reaction between the chitosan and cellulose. We also analyzed the morphology of the obtained aerogel using FACM. In figure A, we can see the CNF aerogel was self-aggregated into porous and sheet-like structure. This structure was commonly observed for nanocellulose-based aerogel fabricated from a freeze drying method. The freezing process before the freeze drying significantly affected the microscopic structure of the obtained aerogel. This study used medium freezing speed at -80 degrees Celsius, resulting in bundles of CNF aggregates in the obtained aerogel instead of single CNFs. The aggregates were formed according to the direction of the growing ice crystals. During the drying process, the CNF was entangled and formed hydrogen bonding with each other, leading to sheet-like structure formation. Similar sheet-like structure were also found for all aerogels. A rough surface covered with light film were observed in figure B, which might be due to the cross-linking reaction of chitosan and cellulose chains. The cross-linking process occurred due to chitosan, which contains amino group reacted with the aldehyde group from the oxidized cellulose and sheath base formation. Nanocellulose-based aerogel is fragile in nature. Therefore, the addition of chitosan through the chemical cross-linking improving the integrity of the aerogel. Kapok fiber with the distinctive tubular-like fiber was observed intertwining the sheet-like structure of CNF as shown in figure C and figure D. Kapok fiber has a hollow structure which contributed to the additional pores in the aerogel. In addition, CNFs clogged the kapok fiber by assembling thin sheet and behaved as a binder and basic skeleton to boost the porous structure, which increased the pore formation. The sheet-like structure were more packed and narrower in figure C than in figure D, as the ratio of CNF and chitosan increased from 1 to 3 to 1 to 5. The introduction of kapok fiber in the aerogel increased the density and the formability of the aerogel. So we tested the oil absorption capacity of the aerogel using two different oils, used cooking oils and used motor oils. The absorption capacity of the aerogels was varied from 9.5 to 38.14 gram per gram. In general, considering the hydrophilicity state of the aerogels in the study, the aerogel showed comparable absorption capacity to hydrophobic aerogels. A015 or CNF aerogel achieved a maximum absorbency of 38.14 gram per gram for used cooking oil. Meanwhile, the minimum absorbency of 9.5 gram per gram was achieved by A015Y or CNF chitosan aerogel for used motor oil. We can see that the absorption capacity of AKAX or CNF chitosan and kapok aerogel with the ratio CNF and chitosan 1 to 3 was 26.56 gram per gram for used cooking oil and 27.3 gram per gram for used motor oil was higher than AKY, CNF chitosan kapok with the ratio CNF chitosan 1 to 5, which was 24.58 gram per gram for used cooking oil and 23.15 gram per gram for used motor oil. The explanation for this reason is due to the increased concentration of chitosan, making the aerogel more packed, which lowering the porosity of the aerogels. So the absorption of oil and organic solvent occurred via physical absorption, where the oils and organic solvents are trapped and stored in the pores of the aerogel. A more expansive space between the sheet structure from the aggregate CNF observed in figure A suggests a higher chance of trapped and storing oils in the pores. Therefore, higher oil absorption was observed for CNF on the aerogel. The addition of chitosan, which although increased the integrity and formability of the aerogels, also narrowing the space, reducing the porosity, therefore lowering the oil absorption capacity of the aerogel. The CNF chitosan kapok aerogel showed higher oil absorption than CNF chitosan aerogel. This was due to the whole structure of kapok, which increased the porosity and thus the performance of oil absorption of the aerogels. So from this study, we can conclude that the aerogel that was obtained from this study was sturdy, lightweight with high porosity. The high concentration of CNF affected the microstructure of the aerogel to a sheet-like structure. CNF aerogel were fragile, therefore the addition of chitosan through the chemical cross-linking improved the integrity and mechanical properties of the aerogel. However, with the addition of chitosan, space narrowed, reducing the porosity, thus lowering the oil absorption capacity of the aerogels. In addition, kapok fiber has a hollow structure which contributed to the additional pores in the aerogel. And then the absorption capacity of kapok CNF aerogel was in the range of 24.58 to 26.56 gram per gram for used cooking oil and 23.15 to 27.3 gram per gram for used motor oil. The result revealed that the obtained aerogel is a promising candidate for oil absorbent, considering the hydrophilicity state of the obtained aerogel. Okay, that brings us to the end of my presentation. We would like to say thank you for UPD PKS that was fun in the study. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Ms. Dian Burhani, for the presentation. as I see from the participant list, there are Dr. Peter Spetter, Professor from Department for Forest and Environment, HNA Aberystwyth, our invited speaker 5, who already honored us with this lecture yesterday in Climate Smart Forest in Germany. Good morning, Professor. Welcome, and we hope you all enjoy the session. Okay, thank you.
Good morning. Thank you for having the possibility to participate. Thank you very much.
Yes, thank you. Okay, for the next session is the Q&A session for the Miss Dian Burhani, entitled of the study entitled of the potential of kapuk cellulose nanofiber aerogels as oil absorbent. If you have any question, please raise your hand by clicking the reaction below the Zoom meeting. Okay. Okay, Mr. Yudi Dwi Kurniawan, please deliver your question.
Thank you, Ms. Sida, for the opportunity. I'm a bit confused about the hydrogel. I have zero knowledge about this, so probably my question is with strange. Okay, my question is, what is the overall nature of the hydrogel? It is more like hydrophilic or hydrophobic? And the second question is, if you have mixture of water and oil, which material will be absorbed more in your hydrogel? Thank you.
Thank you, Mr. Yudi, for the question. So to be clear, my research is not about hydrogel, but it is about aerogel. Yeah, so the aerogel is
okay. Sorry.
Yeah, okay. So the porous, I'm sorry for the break. I'm sorry for the background, the back sound. So the aerogel is a porous material by replacing the solution in the suspension by air. So the characteristic is the aerogel has a light density, high porosity, and also high specific surface area. So in nature, aerogel is a hydrophilic because the raw material that we use is cellulose nanofiber. So cellulose is still is hydrophilic in nature. So we assume that K-pop has like a hydrophobicity properties in nature. So we assume that when we combine the CNF chitosan aerogel with K-pop, it will increase the hydrophobicity of the aerogel. So basically when we use the CNF aerogel for oil and water emulsion, it will absorb both oil and also water. But to increase, but for the oil selection, for oil selectivity, we have to increase the hydrophobicity so we can get a higher oil absorption performance for the aerogels.
Thank you, Ms. Burhani.
Okay, once more question, please in a short question. Mr. Romi.
Okay, thank you. Sorry, may you explain again how to make a hydrophobic character of your hydrogel, and then how to control the porosity of the aerogel of your material? Thank you.
Okay, thank you. So to control the porosity of the aerogel, there are many parameters, but here I use the CNF constant. One of the parameter is CNF concentration. We also can use the freezing stage before the freeze drying process of the aerogel. Here I use like 1.5% weight per volume of CNF suspension, and then the freezing temperature before the freeze drying is the medium freezing temperature. It was minus 80 degrees Celsius. So because of that, the resulting aerogel has like sheet-like structure. The sheet-like structure. So if you want to a sheet-like structure with the density around like 90%, 0.2 to 0.4 gram per centimeter cubic, and the porosity is around 95 to 97%. So if you want to increase the porosity of the aerogel, you can use a lower concentration, around like 0.5% of the initial concentration of CNF, and also you use the rapid freezing before the freeze drying. You can use it you can use temperature for minus 196. You can use like liquid nitrogen. So with that condition, you can you can obtain, for the resulting aerogel will be like have honeycomb structure. So it will with the honeycomb structure, it will also increase the oil absorption of the aerogel. For the hydrophobicity, so the aerogel in this study is still in the hydrophilic state. So we tested we measure the contact angle for the aerogel, and it is still in the hydrophilic state. So even after the addition of K-pop, the hydrophilicity of the aerogel is still like less than 90 degrees, or so it's like it is absorbed. I mean it was not in the hydrophobic state. It's still in the hydrophilic state. So maybe there will be like a surface modification after this to increase the oil absorption.
Okay, thank you very much for the explanation.
Thank you.
Okay, thank you, Ms. Dian, and for all the participants. I'm sorry, Mr. Sasa, there will be only for 2 questions because we have tight time. You can privately contact Ms. Dian for the discussion. Thank you. Thank you, Ms. Dian. Okay, for the next presenter is Dr. Lisman Suryanegara. And he's a graduate from Agriculture University in 2000 and graduate his master's and doctorate degree from Kyoto University. And he has been working in Research Center for Biomaterials since 2000. And his expertise are in bio-nanocomposite and adhesive from now on. Okay, today he will deliver a presentation in the title of formaldehyde-free plywood panel bond with natural rubber latex-based adhesive. Okay, please, Mr. Jauhari, please relay the video.
Good afternoon, ladies and gentlemen. My name is Lisman Suryanegara from Research Center for Biomaterials. Today, I would like to present our study with the title Formaldehyde-free plywood panel bonded with natural rubber latex-based adhesive. Wood adhesive is the key of the performance and production cost of plywood panel. There are many wood adhesive in the market such as urea formaldehyde, melamine formaldehyde, phenol formaldehyde, isocyanate, and others. The most used wood adhesive to manufacture of plywood is urea formaldehyde. Around 40 million metric tons are utilized globally in 2020. However, the problem of UF utilization is the very high formaldehyde emission. In recent decades, Bio-based adhesives such as latex and lignin are well developed. The advantage of bio-based wood adhesive are renewable and sustainable. However, the drawbacks of bio-based adhesive are low reactivity and relatively expensive. Natural rubber latex, or NRL, has been used as wood adhesive by mixing polystyrene, co-butadiene, rubber latex as base polymer, polyphenyl alcohol as adhesion promoter, and polymeric isocyanates such as PMDI as cross-linker. In the previous study, RISH et al. In 2009 already succeed developing a formula and product of an NRL-based adhesive with the brand name of Biomaterials. They demonstrated that the addition of 10% of isocyanate into NRL VPA could produce plywood having bond strength that could meet interior standard. And the addition of 15% of isocyanate meet requirement for exterior standard. However, the higher viscosity of NRL-based adhesive eventually result in several problems in wood-based panel manufacturing, such as fast curing, around 50 to 20 minutes during the assembling stage. Here in our study, the addition of dextrine is expected to reduce the viscosity of the NRL adhesive. Furthermore, the incorporation of dextrine as adhesion promoter could provide hydroxyl group into NRL-based adhesive system that is necessary for close linking with polymeric isocyanate. The objective of this study is to formulate and evaluate the performance of NRL-based adhesive as cold pressing adhesive for plywood in the presence of dextrine. The material are used in this study are natural rubber latex with 60% of dry rubber content from Garuda Indo-Pacific, polyphenyl alcohol with 22,000 gram per mole from Brataco, polymeric dipenyl methane diisocyanate, around 30% of NCO group content, Sengon wood veneers, sizing 300 times 300 times 2 millimeter, dextrine, and urea formaldehyde. We prepare and formulate 4 type adhesive A, B, C, D. A is NRL PVA with 15% PMDI. B is NRL PVA with 15% PMDI and the addition of 20% dextrine. C is NIT PMDI and D is NIT UF. The preparation of plywood bonded NRL adhesive: first, glue spread at around 200 gram per meter square and cool pressing at 27 degrees Celsius or room temperature for 24 hours, and then conditioning in 2 weeks at room temperature. Characterization of NRL adhesive properties such as dynamic viscosity, gelation time, moisture content, delamination, and tensile shear strength. This is the basic properties from 4 types of adhesive A, B, C, D. As shown in this table, the viscosity of A, which is NRL PPA with 15% PMDI, is 907 millipascal second. The addition of 20% dextrose, which is the B type, reduced the viscosity to 300 millipascal second and enhancing gelation time from 102 to 158 minutes. This is the dynamic viscosity data. The data are showing the viscosity of 4 types of adhesive. The viscosity of A, which is NRL with PMDI, is suddenly increased from 1,000 to 7,000 in only 15 minutes. However, the addition of 20% dextrin keep viscosity stable at around 500 millipascal second for 60 minutes. The change in functional group of NRL-based adhesive was recorded using FTIR. The NEAT PMDI has specific functional group of NCO group at web number of 2,272. In addition, PMDI show typical peak of CO, CH2 group, and CC at web number of 1,728, 2,954, and 1,520 respectively. The incorporation of PMDI and dextrin into an RL PPA mixture alter the functional groups of the adhesive. The pre-NCL group and urethane group were identified in NRL-based adhesive mixed with 15% PMDI. Furthermore, the addition of 20% dextrin into NRL PPA with 15% PMDI resulted in complete reaction of NCO group of PMDI with OH group of NRL PPA and dextrin. Moisture content was obtained by dividing the initial and final mass after drying at 103 degrees Celsius for 24 hours. Meanwhile, the lamination test was determined according to type 1 and type 2 method. The maximum moisture content based on GAS standard is 14%. Based on this data, plywood bonded with NRL-based adhesive, which are A and B, met the requirement of JAS because the moisture content below than 14%. Plywood bonded with NRL PPA, 15% PMDI, and 20% dextrin had 5 times greater delamination compared to plywood bonded without dextrin, owing to hydrolysis of dextrin. By contrast, no delamination occurred in plywood bonded with NEAT PMDI and small delamination for UF bonded panel. Tensile shear strength of plywood was evaluated by UTM 50 kN at cross speed of 2 mm per minute. Dry TSS values was obtained by directly testing the sample after conditioning, while wet TSS was tested after immersing the sample in hot and cold water. Dry TSS of plywood bonded with an RL-based adhesive, NEAT PMDI, and UF resin were higher than the requirement of JAS standard, with minimum value of 0.7 megapascal. However, none of NRL-based adhesive could meet the minimum requirement of wet TSS. As conclusion, this study suggested that NRL PVA with 15% PMDI and 20% dextrin could be used as formaldehyde-free plywood adhesive for interior application and dry condition. Incorporation of PMDI and dextrin into NRL VVM mixture alter the functional groups of the adhesives. Authors are grateful for the support from iLab, Research Center for Biomaterials, Japan Society for the Promotion of Science, and JSPS Alumni Association Indonesia. Thank you.
Okay, thank you, Dr. Lisman Suryanegara. Have you joined with us in this room? Please give me a sign. Oh, yes, yes. Okay. For all of the participants, please, if you have any question, please raise your hand. Okay. Oh, Mr. Yudi Dwi Kurniawan, please deliver your question in shortly way.
Thank you. I have a question. I don't remember which slide, but the slide has the FTIR spectra. So I see the structure of two reacting system, which for me, I still don't understand. Could you please explain more? Probably it is between the latex and the hydroxyl group moiety. Thank you.
Hello? Okay, you mean between latex and polyphenol alcohol?
Oh, yes, yes.
That's only the hydrogen bonding. Yes, it's only hydrogen bonding. Polyphenol alcohol and latex, only hydrogen bonding.
Okay, so thank you.
Okay.
Okay, we open for one more question. If anybody here wants to ask something to Dr. Lisman, please raise your hand. Okay, thank you very much to Dr. Lisman Suryanegara because we have a tight time, so we want to move to another presenters. Okay, for the third presenters today is Dr. Yudi Dwi Kurniawan. He was graduate from Universitas Brawijaya and then continue his master in Brawijaya and also the National Central University, and he has recently finished his doctoral study from Monash University. Okay, he will deliver his study about the versatile size to blah blah blah. Is quite difficult to mention. Okay, IT, please play the video.
Hello everyone, thank you very much for the opportunity to talk about our work with the title of Versatile Access to 135 Tri-Substituted 5' hydroxyimidazolidine 2,4-diones, or you can call it fully substituted hydantoins from alpha-keto acids and carbodiamides towards the synthesis of marine thermochromic polyandrocarbamide D. This work has been done by myself, Yudi, under the supervision of Professor Patrick Permuter. For the introduction, I will talk briefly about hydantoin. So hydantoin is organic compound derived from glycolic acid and urea, so that this molecule has another name as glycolyl urea. Hydantoins are classified based on the different level of substitution, and from literature you can find hydantoins with substitution at the position of at number 5', 1', 3', and 135. And the next class of hydantoins are aryl alkylidine hydantoins. These hydantoins consist of aromatic or aliphatic substitution with the olefin at this position. And the next class of hydantoins are aminohydantoins. These hydantoins consist of one extra nitrogen atom at the position number 5 or number 3 and also number 1. The next type of hydantoins are fused hydantoins. These hydantoins consist of two rings combined together, and the special type of these hydantoins are spirohydantoins. These hydantoins consist of two rings connected with one carbon only. Hydantoins have different types of variation, and some of them are exemplified in these slides, such as herbicidal hydantocytin, anticonvulsant phenytoin, cytotoxic 3' diimino 3' oxoaplicynopsin, anti-inflammatory hymenealdicin, and also antihistamine disbacamide and thermochromic polyandrocarbamide D, which is the compound that we will talk more in this presentation. Further, I will talk about thermochromism. Thermochromism is the reversible change in the color of a compound when it is heated or cooled. And to get more idea about what it is, I give example here. So this is a mug that will change color upon addition of hot water. So thermochromic materials are materials that can change color reversibly with changes in temperature. And usually there are four types of materials used in thermochromism, which are organic and inorganic compounds, also polymers and salt gels. And for organic compound thermochromism, there are three reasons of why this phenomena occur, which are variation in the crystal structure and also stereoisomer and molecular rearrangement. In 1994, Pietra and co-workers discovered new compounds, namely zizin, from marine sponge Ziza massalis. This molecule is yellow in color and became colorless upon treatment with methanol. However, the yellow color could be regained upon treatment with heating. Zizin also changed to colorless upon treatment with water, and the yellow color also can be regained after heating. Upon treatment with water, zizin also transformed to another compound, compound 1,1, after the replacement of the sulfur atom here to oxygen. And compound 1,1 also has a yellow color. Interestingly, treatment of compound 1,1 with methanol and water also lead to the disappearance of the color, and upon treatment with heat, the color was regained. And one of the molecule involved in this transformation is polyandrocarbamide D, which is also isolated together with zizin. And this color changing phenomena represent as the first thermochromic system isolated from the marine source. To date, there are no reported work to synthesize any of these molecules, so that in our work we decided to achieve the first total synthesis of polyandrocarbamide D. We come to the next part of this presentation, which is the discussion. So there are a lot of methods in the synthesis of hydantoins, and we were interested in the one developed by Voluntaria, which is the synthesis of hydantoin from carbodiamide and carboxylic acids. There are two types of carboxylic acids used in the Voluntaria method, which are carboxylic acid with alpha bromo substitution and unsaturated carboxylic acid with electron withdrawing group at the beta position. And upon our effort to synthesize xeragosic acid in our other project, we unexpectedly discovered a similar reaction to the one developed by Voluntaria. So we found that treatment of alpha keto acid with carbodiamide could lead to the formation of 5-hydroxy substituted hydantoins. And the proposed mechanism for this transformation is first the anion of the carboxylic acid attack of the electrophilic carbon of the carbodiamide to form the isoacyl urea compound C, And this molecule transformed intramolecular rearrangement to compound D, and the nucleophilicity of the nitrogen here lead to the cyclization to form the hydantoin compound E. And with this newly discovered reaction, we hypothesized to synthesize polyandrocarbamide D from the corresponding precursor, carbodiamide 3 and 3-indole glycolic acid 2D. We also use different type of carbodiamides to understand more about this reaction, and some of them are commercially available and some of them we need to synthesize in our laboratory. And we also use different type of alpha keto acids, which all of them are commercially available. So first we need to synthesize our carbodiamide 3E from the corresponding alcohol and amine. So first we need to convert this 2,4-dimethoxybenzyl alcohol to the corresponding azide by treatment of this alcohol with diphenyl phosphoryl azide in the presence of base, which is DBU, in dry toluene, and the product was isolated in 90% yield. And we also need to convert this amine to the corresponding isocyanate by treatment of this amine with saturated aqueous solution of sodium bicarb and triphosgene, and the product was isolated in 90% yield. And then we combine these two molecules under azotic condition to get the desired carbodiamide 3E in about 80% yield. For the synthesis of carbodiamide 3F, we apply different approach, which is using desulfurization reaction. For this purpose, we will need to synthesize compound K from benzylamine J. There are 3 reported works for this transformation, but none of them work in our laboratory, so we decided to apply a slightly longer step. So first we treat the benzylamine with carbon disulfide in the presence of bog anhydride and DMAP, and we isolated compound L, the isothiocyanate, in 86% yield, and then we treat this molecule with benzylamine to get the compound K in 82% yield. And then for the next step, we need to remove this sulfur using this reagent, namely Mukayama reagent, to get the desired 3F in 34% yield. We also synthesize a highly reactive carbodiamide with bog protection from the corresponding thiourea. So we treat the thiourea to the excess of base and bog anhydride to get the dibog thiourea, and then similar to the previous presentation, we use Mukayama reagent to desulfurize this molecule to get the desired carbodiamide 3D. However, this molecule is really reactive, and we were unable to isolate it, so that we use these additives without prior purification. So we go to the reaction between the alpha keto ester and our carbodiamide. So the reaction of compound 2A and 3A, we isolate compound 4A in 95%, and reaction of compound 2B and 3B resulted in the formation of compound 4B in 88% yield. Reaction of compound 2C and 3B resulted in the formation of compound 4C in 93% yield. Reaction of compound 2D and 3B resulted in the formation of compound 4D in lower yield, 77% yield. However, treatment of compound 2D and compound 3D didn't form the desired compound 4E. Similar observation also occurred between the reaction of compound 2D and compound 3D. Compound 4F did not form. Reaction between 2D and 3E resulted in the formation of compound 4G in lower yield, 50% yield. And for the last combination, reaction of compound 2D and 3F resulted in the formation of hydantoin 4H in 52% yield. So this is a compound that we got. So for the next discussion, we will talk about the protection of hydantoin relevant to the polyandrocarbamide D, which are 4D, 4G, and 4H. However, most of the reaction didn't get what we want, so we highlight 3 reactions here. So treatment of 4G with TFA in anisole, we could deprotect only one side only to get compound 9, and treatment of 4G with strong Lewis acid could not lead to the deprotection of this protecting group. We only got thioetherification reaction. We got compound 10 in about 80% yield. And for compound 4H, it is typical to cleave the benzyl group using hydrogenolysis. However, we were unable to get the cleavage. What we got is the mixture of salt, which consists of compound 11 and compound 12. So for the conclusion, we discovered new reaction of the formation of hydantoin from carbodiamide and alpha keto acid simply by heating in a polar solvent, and we were unable to deprotect our derivative of polyandrocarbamide D to polyandrocarbamide D. So that is our presentation. Thank you very much for your kind attention. Thank you.
Thank you very much, Dr. Yudi. It's kind of interesting study. And there is, okay. Dr. Sasa Sofyan Munawar, if you have any question, please deliver it shortly. Thank you.
Okay, thank you. So the results of this research are very interesting, although quite difficult to understand. So I want to like to know for the application, what kind of the products can be produced by using this research result, and what are the advantages over the existing product? Thank you.
Okay, thank you, Mr. Sasa. So the application of this molecule, the polyandrocarbamide D, is for sensor. So it is for thermal sensor that you can see it visibly. So if you have different condition with a different temperature, the sensor will give you different colors. So that is the application. And what is the advantage for the existing sensor is actually I have not come to that one. So in this paper, our purpose is to first achieve the first synthesis of this molecule. Once we got it, then we will think about it later. Yeah. So the main advantage of this reaction is very simple, so that we can do it by simply heating in polar solvent. So you don't need complicated starting material. Thank you.
Okay, thank you, Dr. Yudi Dukrawan. This is the end of the first group of the session. We move for the second groups of the session that will be hosted by Dr. Yudi Dukrawan. Please, Dr. Yudi.
Okay, thank you, Mrs. Vida. It is me again, Yudi. So for the next speaker, we have Mr. Sasa. So Mr. Sasa will be delivering his presentation about effect of fiber content on the physical and mechanical properties of rami stem fiber rigid polyurethane foam composite. So for the IT team, please help us to play the video number 607. Thank you.
Good afternoon, ladies and gentlemen. My name is Sasa Sofyan Munawar. I would like to present our research entitled Effect of Rami Particle Content to the physical mechanical properties of rigid polyurethane foam composite. Now, rigid polyurethane foam widely used for the insulation component of the building and also used for railway carriage wall insulation and for some component on the car. The question in this research, can Rami steam particle improve the properties of rigid polyurethane foam composite? So now we try to find some several study on the use of Rami biomass for the composites. The base fiber of the Rami has used for composites, and some Rami steam that have been sparingly decorticated from the base fiber are usually used for fertilizer and animal feed. Also, the other research was found that the Rami steam was used for polyester resin composite, and also the particle board was developed by using Rami particle and saw good mechanical properties based on the standard. However, there has been no research on the manufacture of rigid polyurethane foam composites using Rami particle as a pillar or reinforcement. Therefore, we would like, in this research, we try to find out the effect of Rami particle on the physical and mechanical properties of composite. In this research, we use the Rami particle for making composite. We mix the Rami and then the polyol. The mixture between Rami and foliar was mixed with the isocyanate, and then pour to the molding, then close the molding for 45 until 1 hour, and we can get the board after that. We use 50 kilogram per meter cubic of density, and we have 5 types of the board or the composite that without the particle contents, 2.5 particle contents, 5% particle contents, 7.5 particle contents, and 10% of particle content. The physical and mechanical properties of the composite were carried out by using the JIS and ISTM standard for measuring the moisture content, water absorption, thickness swelling, and determine the internal board and flexural strengths of the composite. Testing was used 3 replication for each test parameter. Free rise forming was investigated to know the effect of adding Rami particles to the polyurethane forming process. The text-free time was observed that the time it takes polyurethane to stop reacting and the surface is not sticky. We can see here that by increasing the Rami particle in the composite has resulted in the shorter forming time. So from this research, we can find that by increasing the particle content, that the free rise forming will shortly. The density of composites almost meets to the target. We can see here that the between composite without Rami particle and others treatment almost the same density value. However, the density value of the composites tend to be uniform because based on the statistical test, the addition of Rami particle does not have significant effect. MC value shows increase by increasing the particle in the composite. Also, we found the same condition on the water absorption, that the water absorption values were increased by increasing the Rami particle content. In this study, the Rami particle content has a statistically significant effect on the water absorption capacity of the composite. This is comparable to other study that resulted of the water absorption of bamboo cursor composite were in the range of 30 until 80%. The thickness swelling also shows the same trend that by increasing Rami particle, the thickness swelling values was also increased. This result was different from the previous study using treated fiber that saw the value of thickness swelling of the bamboo crusher content was decreased by increasing the untreated fiber contents. The IB standard value was in the range 0.11 to 0.26 megapascal. Here we can see that the IB value was increased by increasing the Rami particle. The same trend we can found on the fractional strength, that the MOE and NOR value of the control with the compared to the composite containing Rami particle was almost the same. In fact, the MOR value of the composite with 2.5% Rami particle was greater than that of the control and other treatment. The results also the same as the result previous study. On the other hand, the addition of a particle did not give a statistical significant effect on the MOR and MOE. As the conclusion, the addition of Rami particle in the composite has accelerated the free rise forming. The physical properties such as moisture content, water absorption, and thickness swelling were increased with increasing Rami particle in the composite. The highest value of MC, water absorption, and TS against the composite without particle were 2.5 until 4 times higher. The IB value was increased by increasing the Rami particle in the composite. The MOR and MOE value of the composite within the addition and without addition Rami particle were not significantly different. In fact, with the addition of 2.5 Rami particle, the MOR value of composite was higher than composite without using particle. The addition 2.5 until 5% Rami particle into the composite saw optimum result in mechanical process. Thereby, the addition of Rami particle in the composite means reducing the use of polyurethane. Hence, the product is more environmentally friendly and can reduce production costs. So we would like to wishing the acknowledge to the LPDP of Ministry of Financial and the National Research and Innovation Agency of Republic of Indonesia for the financial support for this research. And also we would like to thank to JSPS Alumni Association Indonesia, JAI, for publication support for this research. Thank you very much for your kind attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Mr. Sasa, for the interesting presentation. So we come to the Q&A session. So please, participants, if you have questions, raise your hand. Okay. Well, Prof. Subiata, please deliver your question. Thank you.
Thank you very much, Pak Yudi. Thank you, Pak Sasa, for the presentation. The addition of fiber increased the internal bond strength. Yeah, I think this is a good result. But for the MOE and MOR, the addition of the fiber not significant, slightly decreased. Yeah. how do you explain this result, especially on MOR and MOE? Thank you.
Okay. So thank you very much, Prof. Subiakto, for the question. Based on the data that I saw, for fractional strength of MOE and MOR, so that slightly decreased when the composite was added by particle. But we found that by adding 2.5% of the particle, the MOR value was slightly higher than the control. So the important point in this research, we would like to know the properties when we add the fiber. So based on the structural data, is still good condition. So it's mean by adding the particle, we get almost the same values between the control and then the composite by adding the particle. So it means we'll be reduced to utilize the polyurethane. So the product can be more environmentally and reduce the cost. That's the important. Maybe later I will do some experience. For example, we would like to treat the material, and then we hope we can get more higher mechanical properties compared to another research that after treated the fiber, so the mechanical properties was increased compared to the control one. Thank you.
Thank you very much, Sasa.
Okay, thank you for Mr. Sasa. I think we will be moving for the next speaker, Mr. Ahmad Dinoto. He will be talking about coconut milk cells encapsulation, a model for protecting lactobacillus species. So please, the IT team, help us to play the video number 608. Thank you.
Welcome to my presentation of our study entitled Coconut Milk Cells Encapsulation, a model for protecting lactobacillus species. Today we are facing the problem of COVID-19, and fortunately there's a considerations of the probiotic and COVID-19's links. Several comorbidities were reported related to COVID-19, such as cardiovascular and diabetes, and those are mostly found in the patient of COVID-19. In relation to the those comorbidities, there are relationship with the probiotic, where the probiotic can reduce the cardiovascular disease and also diabetes risk of factors such as elevated blood pressure, serum cholesterol, obesity, and insulin resistance. And new concepts of the gut-lung axis, where the interaction between the human gut and lung, which is the potential positive immune response triggered by prebiotic and prebiotic. Probiotic can produce several substances that can stimulate the lung health and also can boost the immune system. Several bacteria such as Bacillus, Lactobacillus, Bifidobacterium can increase the natural killer cells activity, the helper cells, cellular immunoglobulin A concentrations, interleukin 10, and also increase the level of the interferon alpha. However, there's a problem. Not all bacteria can successfully pass through the gastrointestinal tract. In the gastrointestinal tract, there are several environmental barriers, such as the low pH in the gastric and bile salts exposure in the small intestine. The issue of the cell death during passing through in the gastrointestinal and room storage can be considered for finding the model of the encapsulation. The new model of the cell protections against the environmental barrier is challenging by using the bacterial models, including the Lactobacillus plantarum from plant saps. This bacteria is the plant origins, and another is human origin Lactobacillus fermentum from human feces. The conventional model of probiotic cells encapsulant have been investigated by many investigators, including the material such as starch, alginate, chitosans, whey, hydrated gelatin, xanthan gums, soy protein isolate alginate. The new synthetic model of probiotic cells encapsulated has been developed by Critedent using the film-forming protein carbohydrate emulsion by Maillard reactions and spray drying process. The question is there any natural matrix consisting of protein carbohydrate oil emulsions can be used for encapsulating bacterial cells? We thought that coconut meat can be considered as promising natural sources as encapsulant. Coconut milk is extracted from the coconut in the sap that consists of the protein, carbohydrates, and fat. And the issue of the viability of coconut milk cell encapsulation models is important to be clarified against the heat stress during process, low pH, bile salts, and storage at room temperature. The objective of the study is to develop a model of cells encapsulated with coconut milk as natural emulsions of protein, carbohydrates, oil for protecting lactobacillus. This slide shows the methodology starting from the preparation of coconut milk, pre-treatment and culturing of bacterial cells, encapsulation of bacterial cells using the coconut milk and spray dried. And the last one is the measurement of the viable count. The second step is observation of the encapsulated cells by scanning electron microscopy, and we continue to characterize the encapsulated cells survivability under exposure of very low pH, bile salts, and also during the storage at room temperature. What the results? After spray drying with the inlet temperature at 165 degrees Celsius and outlet temperature at 35 5 degrees Celsius, we count these encapsulated cells in the form of the particles. The particles are homogeneous. When we observe under scanning electron microscope, you can see here the cells is encapsulated very well. We can see the shape of cell here with higher magnification. We can confirm that encapsulation was successful. What the effect of the low pH? The left side here is the free cells without the encapsulation. The right side data is spread right cells. You can see here the free cells in the condition of the normal pH at about the 10 power 10 CPU can be reduced to the 10 to the power 6. The reductions happen in this study due to the toxicity of the pH. When we see in the spread-dried cells or encapsulated cells, there's no significantly changes as we compare in the normal and low pH conditions for Lactobacillus plantarum and Lactobacillus fermentum. The effect of biocides can be observed in this study. You can see there's no significant change when we observe viability of encapsulated cells in the presence of biocides and the presence of 0.3% biocides. It means that the matrix can protect the both Lactobacillus plantarum and fermentum cells. We also observe there's no changes in higher value of viable cells during storage for 4 weeks at the room temperature at about 22 degrees Celsius. Our results also show even though there's a little decrease in viability of Lactobacillus and Lactobacillus fermentum, the cell number is still acceptable at about 10 power 8 colony forming unit per grams. Finally, we can conclude that the encapsulation of Lactobacillus plantarum AP1 and Lactobacillus fermentum A0014 cells with coconut milk as the natural emulsion of protein, carbohydrates, oil was successful. The coconut milk spray cells of Acea lactobacillus species survive in acceptable cell number at about 10 power 8 colony forming unit, and the encapsulated cells were relatively more stable in the viability than those of non-encapsulated cells under the exposure of low pH and salts as well as during storage for 4 weeks. That's all my presentation. Thank you for your attention.
Okay, thank you very much for the presentation, Mr. Tinoto.
Yes, I'm here.
Okay, thank you for your coming live. Okay, we are coming to the Q&A session. So for participants, please raise your hand if you have a question. Okay, I think I have one question for you, sir.
Okay,
so, the preservation effect of this coconut oil to the cells, do you know how long it is? Is it have the expiry date or something like that? Thank you.
Yes, thank you for the question, Pak Yudi. Yes, of course, there's further expired. Why we also observe about the storage. Why we observe the storage? Because normally probiotic is used in the food, and normally if we don't use the encapsulation, it's only about the 2 or 3 days. When we applied, the encapsulation gets longer in the presentation, and our study showed that 4 weeks is still stable. And I think it's quite good news for industry that can apply this model that can just prolong without any influences of the room temperature and also the impact of the oxygen exposure during storage. That's our idea.
Okay, sir, thank you very much. I
You're
think
welcome.
because of the time, we should be moving on for the next speaker. We
Okay,
have,
thank you so much, Chairman.
thank you, sir. So we have Ms. Bunga Yuli Nabila. She will be presenting about analysis of high magnesium nickel slag powder as a supplementary cementitious materials for high strength concrete. So for the IT team, please help us to play the video. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. It is an honor to be here. Let me introduce myself. My name is Bunga Yubi, and I'm from Trisakti University, Indonesia. In this opportunity, I would like to present you about an analysis of high magnesium nickel slag powder as a supplementary cementitious material for high-strength concrete. In the city of Southeast Sulawesi, Kabena Island, a survey was carried out and confirmed that 80% of the island has a very large nickel content and a very high level of nickel. In every year, PT Inco produces a relatively large amount of solid waste in the form of nickel slag, which is around 70,000 up to 72,000 tons, and of course, PT Inco is located in Sorako, South Sulawesi. Nickel slag is a waste from the nickel processing industry in the form of hot liquid, which is then cooled and formed natural rock consisting of solid slag and porous slag. Production of nickel ore is around 40 million tons each year, and around 30 million tons will become a nickel slag. There's the picture of nickel slag landfill in Southeast Sulawesi. In this study, a test was conducted to investigate the performance of high-strength concrete made with nickel slag powder as a supplementary cementitious materials. Many parameters affect the comparative strength of concrete. High-strength concrete is designed to have a higher workability, higher mechanical properties, and higher durability than normal concrete. To analyze the effect from nickel slag powder based on slag amount for supplementary cementitious materials that will be reviewed by compressive strength and microstructure of high-strength concrete. The nickel slag used in this study was provided by PT Indovero with a size of smaller than 0.075 millimeters, which is in the form of powder or commonly called nickel slag powder, or NSP. Cement we choose as a comparison material is OPC type 1 originated from PT Indocement di Garuda. Cement has an adhesive and cohesive character that used for binders which react with water and used as a concrete mixture with coarse aggregates and fine aggregates. The water was taken from the laboratory facility of PT Jaya Beton Indonesia. The coarse aggregates come from Mount Sindur and fine aggregates come from Mount Sudamani. Coarse aggregate maximum size of 5 millimeters and fine aggregate at maximum size of 20 millimeters. To reach a great workability, super plasticizer type Sika Viscocrete 8015 was added as an admixture. Calculation of concrete mix design refers to SNE 2000. Although this regulation only regulates the mixed design of high-strength concrete using fly ash is one of a pozzolanic material, while NSP was categorized as a pozzolanic material, which has been confirmed by the results of X-ray diffraction analysis. Based on the ratio of water-cement ratio with superplasticizer, the water-cement ratio was set at 0.31. The mixing method starts with 100% coarse aggregates and fine aggregates in saturated surface dry condition, and 100% cementitious materials in dry condition were added. Mix approximately for 3 minutes. Next, add 50% water and 100% super plasticizer was slowly poured in. Thereafter, 50% water were added. Mix for approximately 6 minutes. And then the concrete ready for slump test. The slump test was done after the wet mix is homogeneous. Workability test using slump test with Abrams cone. And slump was allowed to reach more than equal to 200 mm for high strength concrete with super plasticizer according to SNE. Samples was put in the water or usually card water curing with a temperature of 20 Celsius degrees until the concrete has reached the age needed for the test. Each of the concrete specimens were tested at 3, 7, 14, and 28 days. And the compressive test using a pilot press digital compression device with capacity of 2000 kilonewton. SEM was performed on one sample, namely 30% NSP for the age of 7 days. For 30% NSP sample, cylindrical samples are cut using bar cutter until the sample has a very small and thick dimension. After the sample was cut, mesh the sample using abrasive paper. After the surface of the sample is very smooth, the sample is ready for SEM. And then the ED is served to identify the mineral content in the sample being tested. The last chapter is the results of the research. Based on the results of the compressive strength obtained, it can be seen that the nickel slag powder gives increased strength to each substitute. The compressive strength value increases until the concrete age of 14 days. At the concrete age of 28 days, 5% NSP and 10% NSP got a higher compressive strength results than the reference. The higher strength result of the NSP substitution concrete is due to the pozzolanic reaction of the nickel slag powder. For the scanning electron microscopy test, it can be observed on the 3000 times magnified nickel slag powder that the nickel slag powder has a sharp and irregular shape. Besides, the EDS results show that nickel slag powder predominantly contains silica, calcium, magnesia, and alumina. The first spot is the point where the nickel slag powder gathers, indicated by the high levels of silica and magnesium. The second spot shows high silica where the compound is the same as the compound contained in cement and can form a pozzolanic reaction. Last but not least is the conclusion. First, nickel slag powder can be categorized as an alternative construction material. And the compressive strengths are almost equivalent to reference concrete. The 30% NSP substitution concrete can be used as an alternative concrete because it can be categorized as high-strength concrete and is more environmentally friendly. And it is proven that the nickel slag waste can increase the result of compressive strength. The shape and the texture of the slag also affects the density of concrete. So it can increase the result of compressive strength. And the use of nickel slag powder as a supplementary cementitious material can minimize nickel slag waste and can reduce carbon dioxide emission produced by clinker from cement production. Thank you very much for your great attention, ladies and gentlemen.
Thank you very much for the presentation. So we will be moving to the Q&A session. So participants, if you have questions, please raise your hand. We are still waiting for the question to come. Okay. I think there are no questions for this presentation. So for the next agenda, I will give the microphone to Mrs. Vida Bernard. So Mrs. Vida Bernard, please.
Okay, thank you, Mr. Yudi. And finally, we come to the last of agenda of this seminar. And now we will hear the closing speech from Dr. Akbar Hanif Dawam as the head of Research Center for Biomaterials. Okay, Mr. IT, please play the closing remark video. Thank you.
Excellencies, ladies and gentlemen, we have reached the end of the first international conference of Lignocellulose, Icon-Lig, in conjunction with the 10th International Symposium for Sustainable Humanosphere, ISSH 2021, that organized together by JSPS Alumni Association of Indonesia and Research Center for Biomaterials. By having this conference, we have to keep in mind this is a very special opportunity for us to go together, keep motivating with innovation and idea dealing with lignocellulose and humanosphere science. I would like to thank to all keynote speakers, invited speakers, and participants who have done outstanding sharing with us. Your sharing, your insight, and your experiences in this 2 days conference are a valuable knowledge for us. I would like to thank the JSPS Bank Office and JSPS Alumni Association of Indonesia for their great contribution and financial support. I also would like to thank the support from RISH-Kyoto University, Japan, and other participated institutions such as National Institute of Aeronautic and Space, IPB University, Universitas Islam Indonesia, Universitas Jambi, Universitas Lambung Mangkurat, Universitas Mulamarwan, Universitas Padjajaran, Universitas Trisakti, and others. Last but not least, I greatly appreciate to all those who have been involved in the organization of the event. Last, we look forward to seeing you again in the next year event. Thank you.
Okay, thank you. And ladies and gentlemen, before I close the session, please enjoy this video that we, the organizing committee, prepare for you. And IT, please play the video. Thank you. Okay, thank you very much. It's an touchable video for us, hopefully for all of you, for all the participants. And now it's time for me to close our session and happily end the first international conference of Lignocellulose that is held in conjunction with the 10th International Symposium of Sustainable Humanosphere. I thank you very much for your uninteractive interaction in this session and such a joyful environment. Okay, for your information, we understand that some of you may require the program book for your professional interest. Therefore, we will update the program book, especially for the authors, title, and also abstract, following the final version of your paper that will be published in our Scopus Index proceeding. We will send the program book by your registered email. Therefore, please kindly check it, especially at the beginning of October 2021. And the second one is, as for the certificate, we will complete, then send it to your registration email before the end of September 2021. Before I close this session, is there any question from the participant? Please raise your hand. Okay, if there's no question, I would like to officially close this session. And thank you for your participation. We are also grateful to share and enjoy this moment with you, and have a great rest of your day. Thank you very much. And to all of the participants, you may leave this room from now on.
Okay,
Thank you.
thank you.
Okay. Let's hear.